Is it too loud? Is it too loud? ¿Es muy fuerte o está bien? ¿Está bien? I'm not in a hurry, so. But I need 1 hour.
I'm not going to cut you off.
I promise to be on time.
I'm going to disappear at 12 o'clock. I have to have a dentist appointment, but I'll then be back in an hour. So nothing dramatic, but I hope yes.
You hope? I don't know if maybe someone should send a message to Ben just to check if he's.
I don't even have his email.
I am actually kind of concerned. I wonder if I should just drop back. Can you let me know? We'll give his best lecture ever.
I mean, he was I don't know, nervous is the word, but obviously in his head preparing his lectures for today, yesterday night. So I think with that level of effort, you're not gonna, he's just gonna miss your talk, I think.
It's totally
I
fine.
think it's going to be here. But I don't know where everyone is. It's very empty. We should start anyway because it's not bigger. So good morning. Welcome to the last day. The crowds are thinning out. Curiously, the ones who were out very late yesterday, they are basically all here. Half crowd is here. So now it's Amy chairing the session and then Angela
Everybody already knows Angela, so please, Angela.
Yes. So, good morning, everyone. I know that my talk is about star cluster formation in the first billion year, very pretentious. But I thought to still go back to what we have been hearing these days to put again star cluster formation and evolution into context. And so I did my homework and went back and looked at the Monday lecture. I was not here. And I'm showing here one of these large associations that Nuria presented on Monday. And I wanted to drive your attention to the size of this star-forming region composed of many smaller clumps, star clusters, sorry, all aggregated in this coherent structure in space and time. So then for the extragalactic studies, and also yesterday Ignacio showed a lot of star-forming regions where very compact star clusters sit inside and they are creating their beautiful bubbles. massive cluster of 10 to the 4, 10 to the 5 solar masses. So this all limited anyway to Milky Way and local group studies. But in extragalactic analysis, so far we have been limited to optical wavelengths or ALMA. So in a sense, the slides, the presentation I gave you was very much biased to optical wavelengths. But actually with JWST now, we can look at the same wavelengths and at the same structures that have been introduced during the 4 days of this school. So before I jump into the JWST result, so this is what we see when we try to combine star cluster catalogs with giant molecular clouds catalogs. And what we see is that young star cluster GMCs are correlated at scales smaller than 100 parsec and at ages shorter than 10 million years. So in the case of this study, the pertinent to 2023 done in M33, they suggest that the giant molecular cloud lifetime is quite short. It's roughly 10 million years, which is in agreement with what we have heard also from the theoretical and analytical point of view in Mark's lecture. And, but also they discuss that the leftover gas of these giant molecular clouds is consistent with the drifting away from where the star cluster are. So essentially the spiral arm is passing. And then the clusters stay behind while the gas continue in its flow. This is similar. This was another study done combining star cluster giant molecular clouds. And you see that on time scales longer than 10 million years, there is no association between the two. So this is how many clusters are found within a certain radii as a function of the cluster age. And then you see that when we look at 100 million years, no young clusters are associated anymore with giant molecular clouds, as it should be. So with JWST, we can finally find embedded. You see the team, this is one of the early FANGS results. They use some mid-infrared color to select the space of the embedded cluster, and then they propose some color cut to actually find them in the galaxies. And here, to give you a context, at the 15 megaparsec, each pixel corresponds to roughly 3 parsec in resolution. Then there are studies of these beautiful mergers, and then you see this is the HST view of NGC 3256. And when we look with JWST, it's actually spectacular, because we are finally looking behind the wall of dust, and we can see all the star cluster forming in this galaxy. So here now, these systems are quite rare. So this is actually one of the closest major merger we can observe, and we are at 40 megaparsec. 1 pixel is 10 parsec. So the resolution is roughly 15 parsec if we think of the PSF. Again, we can use now JWST band to isolate where are the embedded star cluster. And you see in this study, Linden proposed a color cut to find the embedded star cluster. And they find them in this galaxy. They found several hundreds of them, which were not known with the HST. I apologize for the advertisement. This is my program. And here we use the Paschen alpha emission, the PIH band, so the band that traces PIH, to actually detect embedded star clusters. So this is NGC 628. The FANGS field of view is much smaller. Our mosaic covers. And we are at 10 megaparsec. So here each pixel is roughly 1 parsec. You see the contours show you the extent of the 3.3 PIH emission in the ISM, and the circles with different color, I will explain you in the next slides, show where are the star-forming regions. And each of these circle, the size is roughly 10 parsec in diameter. Yes, Sammy?
Could you just give me a little bit of context of the mass of this galaxy
Yeah.
compared to the Milky Way morphology, just because I'm super interested.
Yeah, this galaxy is a pure spiral arm system, so it doesn't have bars. It has a small bulge, which we still see in the blue light, because this is near infrared wavelength. And the mass is several times 10 to the 9. It's a lower mass than the Milky Way disk. Yes. So then we can also look at other regions. So now the contour here shows the ALMA CHO. So we are looking at the one cloud, GMC, in this galaxy. And then we find a lot more clustered regions. So it's like if you imagine Nuria star-forming regions with the many clusters within the 150 parsec is something similar. But now we are looking at this at 10 megaparsec. So in red, I show the cluster that we called EYSCI, AC1, sorry, Emerging Young Star Cluster Class 1. Those are the clusters where we see peak in emission in both the hydrogen emission tracer, so in Paschen alpha and bracket alpha, as well as in the 3.3 micron PIH emission. In orange, I show the peaks that we detect only in the hydrogen emission, and this we call it class 2. And in green are peaks that we see only in the PIH emission, and we actually retain them. We don't give them a class because we don't know what's their nature. I include in this also the young star cluster we have detected in AGC 5 million years. And there you see that some cluster coincides still with these embedded regions. So telling us that the expulsion, so the destruction timescales of giant molecular clouds is actually not instantaneous, and it takes a while, as we all know. So it's also interesting to see the LCDs in the near mid-infrared. So these are average LCD. You can focus on the symbols. And you see that as we move from the class 1 to class 2, the class, essentially, we see similar continuum, although they change, the dust emission is higher in the class 1 than in the class 2. The emission line is also higher. And if you look at the Paschen alpha versus bracket alpha, this is just observational. We are not tracing any physical property. You see that the ratio it's higher for the class 2. So there is less extinction in them than in the first one. The green class appears to be much more embedded, or maybe lower mass. So we do not discuss them very much in the paper. We are trying to fit them with Seagull. We don't know. They could be clusters which do not have massive stars. We don't see hydrogen emission in them. So it's like, you know, this stochastic IMF sampling of star cluster. Or maybe they are just older, so their massive stars are gone. For some reason, they are retaining their PIH emission. Okay, so we can also look at where are the very embedded one. So we use the Linden selection in a different color, and then we plot it in the color that we usually use for the FIST analysis. And you see this color shows the stellar plus dust emission, while here you have stellar emission. And actually in this color, when you have a PIH in emission, you create naturally a second branch, which is actually quite powerful. We use it to select the very embedded star cluster. All of these points here, which have a slightly different color, which come in applying this selection, are actually dispersed and do not coincide with any emission in the field. So they are not, this is like, the sense of contamination if we blindly apply color cut to extraction in the data. And of course, if we look then at all the selection of the different classes, we see that the very embedded one using the color criteria proposed sit at the top of the branch, and then the rest is coming down. And essentially we are witnessing is the disruption of the PIH emission. Extinction is going down, and we go back to where then we have the HST analysis. So when we combine the optical and this new catalog, we see that essentially we miss roughly 70% of emerging star cluster in optical catalog. So all this phase we have been blind when studying HST catalogs. So then connecting the thread, we started on Monday with this lecture. We had this beautiful picture of star cluster at different ages, both in the Milky Way and in extragalactic galaxies. And now I have divided so you describe what you use star cluster for. And essentially, if we want to put this into context, in this school, we are seeing the star cluster can be laboratories. So we can use them to study massive star formation, binary, stellar populations, and we can also use them to understand what drives, so where feedback is produced, and how much couples with the giant molecular clouds, so the coupling efficiency, for example, the star formation efficiency, many concepts that we have been discussing today. And then I have added here more of people that use star cluster as tracer. So we can look at star cluster populations, derive their physical properties, and then try to understand how they can be used to trace galaxy evolution. Okay, so now we go to the talk of today. And again, I have to apologize because Mirka yesterday showed you how far we have been doing analysis of star formation in high-redshift galaxy using lensing. Today, I will move even further now, adding JWST. So we are going to look at galaxies where proto-globular cluster formed. So we can ask questions, for example, when star cluster formation becomes relevant for the star formation cycle of early galaxies, and how star cluster, or what role actually star cluster feedback plays in reionization, and where proto-globular clusters form. So why do we ask this question? I think this has not been mentioned this week, but if we look at globular cluster CMDs, and then we see, so we focus on the main sequence of turn-off, what we see when we do spectroscopy is that the abundances of these stars actually are anti-correlated or positively correlated. So in the top plot here, you see that the stars which are supposed to be forming in the same gas in a single event have actually sodium, nitrogen anti-correlation, and have sodium, oxygen, for instance, correlation. So we see that there are different chemical patterns in this globular cluster, and actually they are quite common. So this is a plot from 2018. There are a few more data added, but essentially shows you that this chemical, they are called multiple population in globular cluster, or chemical patterns in stars in globular cluster are present mostly in all the old globular cluster of Milky Way and Magellanic clouds, up to roughly clusters which are 2 gigayears old. And then below that age, we don't see any trace of this multiple population, or clear trace, which is still under debate, or really multiple population. So if still we focus on the globular cluster of the Milky Way, because these are, the most ancient star cluster we can look at, what information can we decode from them? Here we are looking at the metallicity of globular cluster in the Milky Way versus their age. And then we kind of see some trends, let's say. We see some kind of enrichment. We see something that goes up like this. So what is telling this to us? We can try to decode the information and to recreate the globular cluster population we see at redshift 0 using cosmological simulation. This is a work done now a few years ago from the eMosaics team. They took Igor cosmological simulation, which I will draw as a pot, and they added what I presented in the first lecture. So analytical description of cluster formation efficiency, cluster mass function, and cluster disruption. And they let cluster form while reproducing zoom in. So this circle shows where are Milky Way halo at redshift 0, and then they go back and trace the assembly history of that galaxy, including the cluster. And unfortunately, the resolution is very low, but all these little dots, colored dots, show properties of globular cluster. So then, for instance, this was already proposed by Forbes and Bridge. I don't know if I say correctly. But the globular cluster which the oldest globular cluster seems to be formed in situ in the major progenitor of Milky Way galaxy, while this sequence of globular cluster seems to have been accreted by the major progenitor. So satellites accreted by the Milky Way progenitor. Of course, not everything works perfectly. Here I show two examples. It's very difficult to reproduce the very old metal regions in the Milky Way. So these are the eMosaics simulation. These are another set of simulations, which is telling us something very important about the way the Milky Way galaxy has assembled. Probably has assembled much faster than these simulations are proposing. So, but can we actually detect star cluster at high redshift? And yes, we can do that. But essentially, we can use the gravitational lens effect of galaxy cluster, the most massive object in our universe. They deflect the light of galaxy which sits behind them. With the Hubble Space Telescope. This is a slide that Matteo kindly shared with me. We see already that, so this is like multiple image, 1, 2, 3, 4 image of the same galaxy magnified by lensing. So there is some kind of stretching due to lensing and also mirroring effects. And then there is the object, the yellow brightest object you see. It's the same cluster over and over again. And therefore, we can derive like the average physical properties. And this is for higher resolution. So we determine that this star cluster is very massive, 10 to the 7. Sorry, this actually is the mass of the blue region. It has a size of 8 parsec and the density. So this is 2 orders of than a globular cluster at redshift 0 around the Milky Way. And so on. So there are several studies already done with HST, but these are studies at redshift 2. So we are looking at cosmic noon mainly. I will skip this because it's very detailed. And we can go now to look at what we can do with the James Webb. So we are putting James Webb glasses. It's not a mirror. I wish it would be a mirror of 6 meters. But here you see, Mirko already shows this galaxy cluster image. This is the early release data, which appeared more now than 1 year ago. And actually with Adelaide, we went and looked at all the stellar clumps. But as you can see, this galaxy immediately captured the attention of the community, because they look really like star globular cluster, right, around the galaxy. And you see, it's not the only one. There are others that show similar trends, but this is really impressive. This is a galaxy at redshift 1.4. And so we extracted the stellar clumps, and as Mirka suggests, so stellar clumps have a much larger size than star cluster. We are tenths of parsec, 100 parsec, and the stellar, also the star cluster around. So all the objects that sit around the galaxy are quite old. This is a color magnitude diagram at redshift 1.4. The globular cluster are already sitting in the outskirts of the galaxy. That they have roughly ages between 1 and 4 giga-year, so they formed between redshift 1.6 and 9, which is quite impressive. And then we derive also their dynamical age, and we see that they are potentially gravitationally bound. So here you see their ages. Here, right here, this is actually redshift 1. So this galaxy is roughly here, and then we are looking star cluster that formed around here. So, yeah, I will skip this, but essentially, if you remember, now I'm plotting the globular cluster of the Milky Way, and we are comparing the two different studies that appeared in the literature. And one proposed that this globular cluster were very rich, so they coincide with the top cloud of the Milky Way metal-rich, but didn't have any metal pool. And analyzing the same cluster, we actually saw that there was kind of a metallicity spread. So we looked a bit better at, so if you look better, if you look into the dirt, what we see is that there is no convergence of the physical properties with both photometry. And so when we look at the posterior distribution, we can say that, for instance, this cluster is a metal pool. So this is for our catalog, and this was the MOLA catalog. It's a metal pool, but we cannot say exactly how much. And it's old, but we cannot say how old, right? So the right way to plot maybe the properties that we have derived, it's something like this with a lower limit on the ages. So they can be as old as the universe. And now you see with both photometry, we derive a similar spread in metallicity. And of course, when we find a globular cluster at this, we can also compare with simulation. Now again, I'm showing the hemocytes, and here you see the growth of galaxy of different mass at redshift 0. And if we plot the properties of the sparkler, we see that it will be a galaxy, that it will be roughly M33 masses, so a few times 10 to the 9 at redshift 0, if we believe this prediction. Okay, so now, if we want to understand the star cluster formation in reionization era, or like 1 billion years after the Big Bang, maybe we should also look at the average properties of galaxies. And this are all results from recent study with the James Webb. So this is the Ainsley paper, and here they plot the equivalent width of combined H beta and oxygen 3 of these galaxies. And as you can see, it's really high. So we are looking at galaxies, especially the one which are going to much higher redshift, that have increasing equivalent width on average. So these galaxies, essentially the equivalent width here is telling us they have a higher specific star formation rate. You know what is the specific star formation rate? So star formation rate per mass. So we are looking at galaxies that are forming a significant fraction of their stellar mass. And also this high equivalent width is compatible with galaxies that are producing higher, they have a higher ionizing photons production efficiency. On average, this galaxy, this is the proposed color, far UV color from Finkelstein, which appeared a few weeks ago. They look at the color into two far UV bands. So the change in color here is simply telling us how much extinction there is in these galaxies. If it's negative, there is no extinction. And if it's positive, so 0.1 correspond to 0.05 magnitude in AV. Essentially, all these galaxies that they are looking in this large field, this is NG deep, are compatible with the very low dust extinction. Their sizes are really small. So now we are looking at the sizes of the galaxies versus their masses and versus redshift. And what we see is that for all the masses that we can derive, these are all photometric determinations, the sizes of the galaxy, the effective, the half-light radii is between 100 and 1 kiloparsec. So it's really, really tiny and compact. And their sizes seems to go down with redshift. And I point out this object, which is really, it's in a lens field, is lensed 8 times, its intrinsic size, and it's really small, so it's 16 parsec, a galaxy of 16 parsec. We think regions, but the authors call it galaxy, so it's in that plot. Okay, then also really interesting with spectroscopy, we see in these galaxies nitrogen enrichment. And to understand how significant this enrichment is, so here the authors show these are the very metal poor dwarfs, H2 regions and or galaxies, nitrogen abundance measurement in this galaxy like green bean-like as function of their nebular metallicity measurement. These are H2 regions in normal galaxies at redshift 0. And you see, we find now galaxies which have actually nitrogen abundances, which are supersolar. Okay, and if you remember, we said the globular cluster have a nitrogen-enhanced population. So maybe this could be potentially the galaxies where protoglobular clusters are forming. Or maybe this could be potentially a phase that these starburst galaxies are experiencing. So there is also something else that comes out of the luminosity function. So here we are looking at the number of galaxies per cubic megaparsec comoving volume, so per comoving volume, as function of their absolute UV luminosity. And again, this is an extreme example. This is redshift 11. Observations show that there is an offset with any of the predictions which were made during pre-JWST result to actually bring all this cosmological simulation into fitting what we observe. We have to assume either that the mass function in this galaxy is top-heavy, so this galaxy actually may be lighter in their mass than we are deriving if they have more massive stars than we assume. They could also be very bursty, and this is they have bursts which are at least 2 sigma above the average star formation rate that we assume at this redshift. There are also explanations. I will not mention all of them, but there could be a larger number of AGNs, no dust, all concourse essentially to push up what we thought we understood from before JWST. So now we move into the star cluster, and we use this lens field, which we are studying together with the team, with Mirka, with Adelaide, the postdoc in Stockholm. And Mirka already showed this clumpiness rate as a function. But so Mirka showed you essentially the stellar clumps properties yesterday up to redshift 5. I'm now going to cover what we see at this redshift. And unfortunately, this is, again, self-reference. There are not but I'm sure that there are people working on this, so they will come soon. So what do we see in galaxies at redshift above 5? So actually, we don't see any more disks, right? This is like a compilation. Galaxy seems to be clumpy, but to not show any regular morphology. And then as we move at higher and higher redshift, here are all magnified galaxies. They are becoming very faint, and maybe they have 2 clumps in their body, maybe none, maybe 1. So it's like the top one. It's a single small galaxy up there. So the sample that we are analyzing contains all of this system. For I divide the class, so the sample at redshift above simply how physical properties differ from lower redshift clumps. So clumps in galaxy at redshift above 5 are smaller, so more compact. They are young. So a trend that Mirka was discussing yesterday is still there, and but they have similar masses to the other clumps that we are finding at lower redshift. So if we do plot the stellar mass of these clumps as function of redshift, imagine that these clumps is where the star cluster are forming. We see that there is a clear age clumps becoming younger as we move with redshift average with respect to the cosmic noon and below. But their mass is not changing, as I already said. You lost me? No. The density is going high up, but it's also here, okay? And again, if we plot the distance of clumps from their center, we see that essentially these galaxies are very small now, and we do not detect actually many clumps above 2 kiloparsec distance from what we think is the center of the galaxy. And here you see how much larger. So this is the size redshift evolution seen with the clumps.
So this is saying that the clumps migrate outward, or is the older ones are the only ones?
Our distance are the galaxy, right? We are not looking at migration here. We are focusing on this type, on this galaxy, so it's really difficult to say there is a migration. There is not even an age difference, but that is, Mirka showed yesterday. What you are seeing here essentially is that the age of the clumps on average is going down as we look at younger galaxy, which is something we expect, and that their clumps are closer to the center because galaxies are smaller. Okay. So now we can also look at the clumps. So we can divide the sample above redshift 5 as one clump galaxy. So it was that example that I point dot for the galaxy. We can look at the center if there are at least 2 clumps in the galaxy, and the other clumps essentially show the properties of the clumps which do not coincide with the center of the galaxy. So when we compare the physical properties, what we see is that the central clumps of a galaxy with at least 2 clumps, older, okay, it's the green distribution, they are roughly more massive, larger, and denser, so which points towards a kind of evolution of the center of these galaxies. Galaxies which are one clump have similar properties to the other clumps in the multiple clump galaxies. Do you follow me? Essentially, what we see probably is that these single clump galaxies are dwarf galaxies where we see simply the clump that is star forming, and we are losing the low surface brightness of the galaxy because it's too faint below detection. That's why we don't see evolution. Did you want to say something?
Yeah, I'm a little confused. So are we supposed to be comparing one clump is yellow?
Yes, with the pink one.
With the pink, okay.
Yeah.
They don't look, I don't know, are they statistically?
Different, no, they are not. So the green one are slightly different statistical, so there is some significance. I don't quote here the probability, but they are different, the green one, from the pink and yellow. And the green one are the central clump of galaxy with multiple clumps.
Okay, so green is actually statistically separable from pink and
yes,
yellow. Okay.
Yes. While the pink and yellow, they are not statistically significantly different from each other. Okay, and finally, sorry, we are looking now at, this is a galaxy cluster field where arc redshift 10 was already discovered with HST. And now with JWST, we see actually that the light, this arc extended 5 arc seconds. It was reported to be 1.5 arc second long before. And so there is a very faint light stretching. It is confirmed to be a redshift 10. We see in JWST now that what was a blobby appearance is actually, there are many little dots. You don't see it at this, in this image, but I will show you other image where the star cluster come out. Essentially, we find in this low mass galaxy, redshift 10, the critical line is crossing, so the arc is actually 2 images, mirrored image of the same galaxy. And then within 0.65 arc second, we find 5 star cluster, or 5 potential star cluster. And in the other image, we can trace only 3 of them clearly, which is something very common for lensing, to see just partial images of galaxies. So what we are doing essentially is analyzing the light, because we have all the JWST bands, photometric, so we can reconstruct the SED of the cluster. And you see, we derive on average clusters which are roughly 1 parsec in size. Their masses is between 10 to the 5, several times 10 to the 5 and 10 to the 6. Their ages are all quite young, so E1, the one closest to the critical line, seems to be the oldest structure in the galaxy. While there are other objects which are quite young, you see the best fit model has strong emission lines, and we see the jump in the filter where these strong emission lines are, so we are confident of their ages. The metallicity are really low, both if we fit it as a galaxy or we fit the single cluster. We don't know if we are reaching now the limit of POP3 population. We have asked JWST time to actually follow up with spectroscopy and understand a bit better the nature of this galaxy. So, but we have the physical properties of the star cluster, we can look at their densities. We have talked a lot about stellar surface density during my lecture and also Mirka. Here you see we plot the clusters with the same symbol. Each symbol is one of the 5 clusters. And then they have different shades if we use a different lensing model. It doesn't matter essentially which model we use. We always find that their surface density are very high. We are looking at more than 10 to the 5 on average with this upper limit. And if we look at the young star cluster in the local universe, their density is much lower. So this is the Brown and Gnedin sample I showed in the other lecture. Here you see the Milky Way globular cluster are sitting here. So we find very small sizes and high densities. I also added other studies where we have been finding the sunrise star cluster. Are these compatible, this cluster we see there, are they compatible with the Milky Way globular cluster? They actually are, if we consider that these are very young, but they have still to go through stellar evolution. So if we assume that it's adiabatic expansion, we can predict essentially that the effective radius at the time t. So if we think at the time 0 local universe, they have lost 50% of their mass, then what we expect is to see that their size will become roughly the size of the globular cluster, so 2 to 3 parsec. So they move here. And also the mass, since it goes down, it can be explained simply with stellar evolution, the offset. Then, of course, this cluster will go through relaxation, and probably, since they are very high stellar densities, they are formed, and they have massive stars. They are forming stellar black holes. So also black hole, the presence of black holes changes the dynamics, the n-body dynamics of the stars within the cluster. So yeah, this is the end of the lecture. I have just some reflections. I think we all agree with the statement that star cluster produce clustered stellar feedback. And so is this the fact that they are such an efficient producer of stellar feedback related with the physical properties that we are seeing in these low mass young galaxies in reionization era? And also to explain why they are so bright galaxies, we need actually to increase their average star formation efficiency. Maybe, and we see that they are also bursty. Are these galaxies forming more massive cluster? So it's like when we discussed what's the maximum mass of star cluster you can form. Maybe in these galaxies, they can easily reach 10 to the 5 and 10 to the 6. We saw that there is nitrogen enrichment. Are the star cluster within this galaxy responsible for it? And so the stars within the star cluster. And also, we don't understand really how landmark continuum escaped from the galaxy and reionized the IgM. And then we can think, are the star cluster the drivers, so the one that produced the Lyman continuum, that reionized the universe, or the conveyors? And what I mean for here is that probably what happens is the star cluster use their energy feedback to open the H2 regions, and then the subsequent star formation, the photons produced in the subsequent star formation are escaping from the galaxies. So I don't have answer for any of these questions, but there is a lot of work to do. So I hope that maybe some of you will follow up on this, actually. And that's it. So I'm happy to take questions now.
Thank you, Angela. Questions? We're bursting with energy this morning, right?
Well,
I didn't get if the sizes of these small things are after PSF deconvolution
Yes.
or yeah,
yes.
okay.
They are intrinsic effective radii, half-light radii.
Okay.
We remove the PSF. Yeah.
So could it be that the JWST is not sensitive to the outskirts of with the smaller surface density?
Well, I mean, the size actually is determined by the core size, right? So where the light is the brightest. It doesn't, so we fit the model to get the light in the wings, but we don't, yeah.
So it's the size of the core. Okay.
Yeah.
I had a maybe naive related question, but maybe it's more about lensing. Is it possible that somehow the sizes are affected by like where the lensing caustic hits a high Z galaxy and you pick up preferentially because it lands on some star cluster?
Yes, definitely. So we are using these two models that, as you see, the critical line is crossing approximately at the same position in the arc, but they predict different magnifications. So we go from magnification of hundreds to 70. So there are variations to the 30%, and that's why we plot both predictions. But essentially, if you are not on top of the critical line where magnification changes instantly, like you move.
The caustic, it's like this huge discontinuity.
If you are not on top of the caustic, then the changes here are not going to affect the fact dramatically the sizes we derive and the masses.
I didn't understand how we can know that it's like a mirror system.
Yeah, because essentially their ACDs are quite similar. So one is the morphology, typically tells you if the critical line crosses, then you expect to be two mirrored images. But also the ACD of the cluster, so here I plot the one we recognized are the same object, are quite similar within uncertainties. So we know that we are looking, so in orange I'm plotting the cluster ACD of image 2. And we derive similar physical properties, so we know that they are likely be the same object. Okay.
We good? We good?
Totally out of left field question. I have no idea if it makes any sense, but it's occurred to me. When you have multiple images, what are the typical delay times that you estimate from the lensing model between them? And are those at all interesting for probing the lifetimes of these embedded clusters?
I cannot answer that question. The late times can be derived, but I don't know, I mean, million years. So for supernova explosions, the delay time between images are of order of years. So you see appearing one image, and then after 1 year, it appears in the other.
Okay, so they're going to be very short. Okay.
Yeah, exactly. But the change in emergence phase is like a few million years. So yeah.
Maybe naive question, but how do you get these ages? Is it from fitting these SEDs?
Yeah, so we are fitting the SEDs. We are using BPAS models, or like we use stellar population. We assume a single burst, and we let then all the other properties change. We include the cloudy, so in the models to also explains the feature we see.
And you're fitting order 6
yeah,
broadband
yeah.
photometry points.
We have a detection in all the 6 bands.
In your opinion about, in this kind of fitting thing, what's like the most obnoxious degeneracy that pisses you off the most?
No, so we tested different star formation history. We use exponential bursts of 1 million year tau, or we use a single burst. We use different stellar population models because the massive stars are different, and we know we are looking at very young clouds. So we use the BPAS and we use the other more normal models with the Chabrier mass function. And in the BPAS model, we have 300 solar masses as a maximum stellar mass and rotation, so the binaries, yeah. But we get very similar masses and ages, and all the properties remain the same. So we are, from SED fitting aspect, they are robust, but I think until we get spectroscopy, it's tough to say, okay, we can trust this percent.
Cool. Thank you very much, Angela.
Perfect. Okay, let's get this show on the road. There we go. Okay, perfect. All right, so thank you, Angela, for kind of introducing us to the world of the first billion years, and quite frankly, introducing us to some of the most interesting stuff in the world of the first billion years. Today, I'd really like to talk particularly, and not just talk at, but with you folks, about what I think is the thing that makes the first year interesting. And it's that fact that in the first billion years of star formation, you are probing both the physics of star formation and the physics of cosmology simultaneously. If you don't understand this, you're not going to understand this. And if you're trying to understand this, you have to understand this. So in some ways, it's very exciting because it's like, oh my goodness, whiz-bang stuff. We all get to work on the entire origins of the universe. In other aspects, it's very challenging because basically no one understands this and no one understands this, so no one understands anything. So let's start not with the first billion years, but with the first 40,000 years, because we're going to have to really start with the beginning here in order to understand what is it that makes the first billion years interesting. So unfortunately, we're going to have to go into the world of cosmology. So for those of you who have taken your cosmology courses, you probably recognize the Friedmann equations here that govern the expansion of space-time in a general relativistic sense. Don't worry if you don't remember these. The thing you really want to remember here is that this scale factor A is just how lengths grow with time. And it's related to redshift as 1 on 1 plus Z. So if you're comfortable with redshifts and not scale factors, just keep this back in your mind that scale factor is kind of like an inverse redshift, but not quite. So if you really want to dive into this too, I really, really love Ryden's textbook. If you're trying to teach yourself cosmology, this is the best place to start. It's, even if you're not trying to teach yourself cosmology, it very much deserves a writing award. It reads like a novel. It's fantastic. Love that book. So as the universe evolves over time, different components within that universe are going to scale differently. So we think that the major components of the universe are matter, relativistic particles, which are primarily photons, this baffling cosmological constant that we call lambda, or dark energy, and potentially curvature as well. But the latest Planck results suggest that omega naught, the density parameter of the universe, is probably close to 1, so most likely you can forget this term. We live in a flat universe. And you notice here that each of these have a different exponent. So for the cosmological constant, there is no dependence on scale factor, which means that the density of dark energy here is constant over time. Meanwhile, matter scales as you might expect. If I have 10 ducks in this room, and I double the size of the room, I've reduced the density of ducks by a factor of 2. So the scale factor to the third power is just the volume. The matter density scales as the volume of the universe. Photons scale a little bit more aggressively with scale factor. They go as a to the minus 4. Does anyone know why it doesn't scale the same way as matter does? Exactly, redshift. So this is kind of the picture we have right now, our best measurements of these cosmological parameters. And one of the really important things that goes on in setting up the initial conditions, really, for galaxy formation is the fact that up until when the CMB is emitted, about 400,000 years ago, we transitioned from a radiation-dominated universe to a matter-dominated universe. We're now in a dark energy-dominated universe, but that is well beyond the first billion years that we're going to be talking about today. So where are we at a billion years after the Big Bang? Well, that brings us back to a redshift of about 5.6, which gives us a scale factor of about 0.15. That means that co-moving megaparsec in physical units, what would be a megaparsec separation today, would be 150 kiloparsecs at redshift 5.6. That means that the matter density of the universe was about 300 times what it is today. And it also means that the temperature of the CMB was around 20 Kelvin. So push that back further into the first 500 million years or so, these numbers are going to go up. And Lucio talked a lot about how the temperature history of the universe during reionization, well, pre-reionization, can impact population 3, star formation. I'm going to try and skip over as much of what Lucio's already covered as possible. So let's step ourselves forward now. We're walking our way towards the first big gigayear. So, got to start at the beginning. So first 10 to the minus 33 seconds or so is when inflation happens. So we grow the universe in size by about 60 e-foldings. So that means A scales by about 10 to the 26. We don't have direct evidence of inflation, but we have a couple of good reasons to think that it happened. And one of the best arguments for it is we need something to set up initial perturbations in the scale of the universe that will eventually collapse to form galaxies. And I won't dive deeply into the physics of inflation because I don't understand the physics of inflation deeply, but one of the things many inflationary theories predict is that we get an initial power spectrum that is just a power law. So the perturbations in the universe scale as a power law in wave number. So in other words, the wave number is the inverse length. The simplest model for this power spectrum gives you an index of 1. This is called the Harrison-Zeldovich power spectrum. One of the many examples, I think, in cosmology of where an initial prediction or theory that was designed simply because of aesthetic or laziness reasons turned out to be kind of right. Planck suggests that this power law index is very, very close to 1. So by the end of the first 10 to the minus 33 seconds, we're out of the inflationary period. The universe is flat, omega is 1, and we have these very, very small fluctuations, initial quantum fluctuations that have been blown up to macroscopic scale. This is really important because these are the seeds for our galaxy formation that's going to start happening. Over the next 20 minutes or so, we have Big Bang nucleosynthesis. This sets up the chemistry of our first galaxies that are going to form. So if you want to go back to the original paper, it's the alpha, beta, gamma paper, alpha, beta, and gamma. Beta actually didn't work on it. They added him just so that the acronym would work, which, again, they did things differently in the 40s. But this sets up our initial chemistry of the universe. About 25% of the primordial gas that's going to start forming galaxies is in helium with traces in lithium and beryllium as well. And as Lucio mentioned, importantly, some deuterium. Then for the next 500,000 years, really from the beginning, we are in the radiation-dominated era. So up until a redshift of about 3,500, the dominant form of energy in the universe is actually photons. That is going to change the way things evolve over time. But after this point, matter becomes the most common piece of the universe. It's the dominant energy form. We're in a close to Einstein de Sitter evolution. And for 400,000 years, this is how things go until eventually those photons and baryons decouple, and we start to actually get evidence of this. So this occurs at around a redshift of 1,000. And this decoupling is the point at which the CMB is emitted. Because prior to this, the photons and the baryons, because the universe is ionized, the Thomson scattering cross-section is high, which means the mean free path for photons is low. The universe is a brick. It's opaque. This is why we don't see past the CMB, is because the entire universe prior to the CMB was opaque. So this is where we're at now, 400,000 years after the Big Bang, but we don't have any galaxies yet. So we know that the CMB perturbations here are on the order of 10 to the minus 5. These are not galaxies, these are temperature perturbations. And when you measure the power spectrum of these on the sky, you can then get those cosmological parameters that I quoted for you earlier. Now, you're probably thinking at this point, okay, Ben said that the power spectrum for matter fluctuations is a power law. Now, we're all astronomers. We've all seen power laws. Does this look like a power law to you? No, it's not a power law, because this is not the power spectrum in linear K space. This is the temperature power spectrum in spherical harmonics. So this is the natural way to measure the CMB on the sky, because you're looking at the entire sky. This is what eventually lets you use things like the height of this peak and the location of these second and third peaks to measure these cosmological parameters. But if you're thinking more about this power spectrum of galaxies, what kinds of galaxies are you going to get forming at what time, you'll want to convert this into something in regular length rather than spherical harmonics. And this is what you get. This is an output from a CMB code using the Planck parameters that tells you the power spectrum, effectively how many galaxies you should be getting as a function of the scale of the patch of the universe that collapses to form them. Now again, I said, you're all astronomers, you've all seen power laws before. Is this a power law? Why is it not a power law? Does anyone know why this isn't a power law? Yep. Yeah, it's not a straight line. But the physics of why is that there's a lot that goes on between inflation and when the CMB is emitted and when eventually galaxies start forming. And that's what ends up transforming this from a straight power law to something that turns over. And in fact, that physics can tell you a little bit about the structure of the universe. So for example, if you change the mass of the CDM particles to be very light, such that they become somewhat relativistic, you can actually suppress power on large K, which is small length. Basically, in other words, if CDM is actually warm dark matter or hot dark matter, we should have fewer small galaxies, and the first things that start to form will be a little bit bigger. So the reason this is not a single power law is physics, basically. So what we're missing here are the way in which perturbations grow between the point where they're seated at inflation and when we see them. And it turns out they don't just grow, they can actually be destroyed as well. So in the radiation-dominated era, the Hubble drag, the expansion of the universe, slows down the expansion of, or the contraction of perturbations. And later on, in fact, right next to the time of recombination, there's a very important effect called silk damping that destroys all of the baryonic perturbations below a mass scale of about 10 to the 15. Silk damping is hard to calculate, but easy to understand. Think about you have a fluid of matter, baryons in this case, that are lightly coupled to photons. And there's a lot of photons. There's more energy in the baryons than in the photons. But you have a tiny linear perturbation, maybe 1 part in a million, in your baryon fluid. And the photons can just free stream. And occasionally they collide. Those free streaming photons are going to wipe out many of those perturbations. Basically, they're going to carry the energy away. And so all of this physics is what ends up going into changing your simple power law into something a little bit more complicated. But I want to ask you this question, because this is, I think, an important thing to understand in cosmology too. If the only baryonic perturbations that we have are on the scale of 10 to the 15 solar masses, why aren't giant galaxy clusters the first things we form? Yeah, that's a brutal one. I was debating, do I ask and be an asshole, or do I just answer it? The reason for this is that silk damping effect only couples the baryons. The dark matter has continued to collapse its perturbations, and without dark matter, we would live in an anti-hierarchical universe, because silk damping would obliterate all of the small perturbations, and the first things to collapse would be giant clusters. Because we have cold dark matter, it continues having its little clumps collapse, and as soon as recombination happens, the baryons just fall into the potential wells of the dark matter perturbations, the dark matter overdensities. So this can all of this physics can get captured in these two functions, your transfer function and your growth function. And I could spend the entire rest of, actually, quite frankly, we could spend a whole day on how you generate these functions, but don't. Just go use a tool that exists out there. No one who's a cosmologist calculates these things by hand anymore. We have codes for doing this. But it's good to know that the way that we get the initial conditions for galaxy formation is a combination of some physics from inflation, which gets you the initial power spectrum, and this transfer and growth function, which is basically all pre-CMB physics. And all of that is going to set up what kinds of galaxies are going to start forming for us. So we've done 400,000 years. Let's do now actual galaxy formation, because up until the point where the CMB is emitted, we're not talking about galaxies. We're not even talking about stars. We're not even talking about clouds. We're talking about perturbations on the scale of 10 to the minus 5 or so. So I want to get us started by stopping talking for a while and starting to listen. So I want to do a brainstorm again here on the board and get some ideas from you folks about what might be different in the first gigayear of galaxy formation compared to the subsequent 13 billion years or so. So let me erase yesterday's brainstorm and start writing some things down. So anyone have any ideas as to what might be different for a galaxy that's forming in the first gigayear versus a galaxy that's forming or evolving maybe in the most recent gigayear? Good one.
I didn't even hear that.
So lower or higher? Yeah. Lower, big Z. Yeah? Temperature in what way? Mm-hmm. CMB is still hot. Yeah. Here's an interesting related to that.
The density of galaxies too?
Sorry?
The density of galaxies? The volume.
Yep, volume density, for sure. Everything's close together because the universe is small. Sorry, Amy, I'm making you run around early.
It's keeping me up after all.
Okay.
More irregular shapes, morphologies in the galaxy.
Yep. Lumpy boys. And we know that observationally, these things are clumpy and lumpy.
There's more interaction with the galaxies or like things around it, so there are more interactions.
That is, I think, the biggest implication of this higher volume density for sure, is we have frequent mergers and interactions. So if everything's closer together, you're going to crash into each other more often, for sure. That's going to be hugely important.
Maybe the cold accretion mode.
So, very good. We didn't really talk much about this, but cold accretion might be important. So, for those of you who aren't familiar with cold accretion, galaxies can accrete gas in two modes, hot and cold. The hot mode accretion occurs when gas shocks when it hits the virial radius of the galaxy, and it's important in galaxies about the Milky Way mass or higher. In lower mass galaxies, the virial velocity is low enough that gas can just kind of stream in the whole way without shock heating. So if we've got small galaxies at high redshift, they're probably accreting through the cold mode.
Higher amount of gas.
Higher gas fractions, absolutely, absolutely. We haven't had as much time to turn that gas into useless old stars. Okay.
I'm assuming also environment is not going to be so much different, like the large scale structures. So it's going to be like more similar galaxies between each other. There's not going to be a differentiation in.
Okay, that's an interesting idea. That's a really interesting idea. So less diversity maybe. So you're not going to have this spectrum between tiny little dwarves and giant clusters.
I have no idea if this would contribute at all, but the relative abundances of dark energy, dark matter, and baryonic matter.
You say you have no idea, but you're absolutely, absolutely correct. One of the major things that affects this is less the first gigayear, but more the first 7 or so gigayears. The fact that the universe is matter dominated for a while is actually essential to forming structure. I'll talk about this in a moment, but structure formation is over now that we're in the dark energy dominated phase. So the fact that we have a matter-dominated universe rather than a radiation or a dark energy-dominated universe is essential. So I'm going to write that down as EDS because we're in an Einstein de Sitter phase for the cosmology.
Maybe the first supernovas, the Barsty phase.
Yep. The early supernova, like POP3 supernova, might be wild compared to regular ones. So I'm just going to write that down as stellar feedback might be different. Stellar feedback. Okay, I think we've got a good number of ideas here. So let's jump forward now. We've talked a little bit about the first 400,000 years. Let's continue on for the next 0.9996 billion years. So now we're going to talk about how we go from this, the CMB that's emitted at around 400,000 years, to this. And I know this is not a redshift 1 galaxy, or a redshift 5.6 galaxy, but unfortunately all of the pictures of redshift 6 galaxies are very uninspiring. They're red lumps. So what we're going to do, and by we I mean like the gods, is grow some initial linear density perturbations into larger scale structures. So these density perturbations are initially very small, so you can use linear perturbation theory. I'm not going to show you how to do that because, again, we want to talk about galaxies, not the growth of spherical top hat perturbations. But know that there are ways to do this and make predictions about what are going to be the first halos to collapse and how many of them are going to collapse. So the big one that you'll probably use in your career if you end up doing any kind of cosmology work is the Press-Schechter formalism. And so if you want to really know them, buy this book. Unfortunately, it's not as readable as Ryden, but it is comprehensive. It is biblical both in its comprehensiveness and its weight. It's like this thick. And so your nonlinear structure formation, whether you use Press-Schechter formalism or n-body simulation, they all tell you something about what kind of halos are going to collapse first. Namely that at redshift 30 or so, you're not going to have in any given patch of the universe that is normal big halos. The first things that you're going to get in high abundance are going to be very small halos, so on the order of 1 million solar masses or so. And that's the virial mass. That's not its stellar mass, that's all of it. So these are tiny, 1 million times smaller than the Milky Way. Thankfully, we're out of the cosmology phase now, and we can start talking about what starts to form inside of these little halos. So to do that, I want to jump from what I'm comfortable with, cosmology and theory, to something you folks are probably comfortable with, spectroscopy, which terrifies me, deeply, deeply, deeply terrifies me. So when we're looking at this, we've got 2 quasar spectra here. One in black here at redshift 6.5, and one in red at redshift 2. And there's a huge gap in the bluer frequencies here, but otherwise these spectra are basically the same. Does anyone know why this high redshift quasar has lost all of its flux at a certain frequency and above? What causes the Lyman alpha forest? What's the physics involved? Who said extinction? Extinction by what? It is sort of. Oh yeah, yeah. Did you get your thunder stolen? I'm sorry. You'll have to fight it out when you get back to Gainesville. So yeah, this is because the universe was once neutral. So the emission of the CMB itself corresponds to a period when the universe went from being ionized to neutral. Ionized gas is opaque to, well, if it's dense enough, dense ionized gas is going to be opaque to all frequencies of light. But diffuse ionized gas is transparent to UV. Diffuse neutral hydrogen is not transparent to any photons that have a high enough energy to ionize hydrogen. So this is the signal, this is your smoking gun signal, that above redshift 6 or so, there was a lot of neutral hydrogen in the intergalactic medium. And beyond that point, nearer to us, there isn't much neutral hydrogen in the IGM. So this is reionization. You've heard of reionization, and this is the kinds of signals that show us that reionization happened and start to tell us when reionization happened. So between the point when the CMB was emitted and the first stars and galaxies forming, the IGM is purely H1. Eventually, though, those first stars, first galaxies, and probably some contribution from early AGN activity as well, convert the vast majority of the IGM from a neutral fraction of 1, down to today, which is a neutral fraction of damn close to 0. It's not exactly 0 because of statistical mechanics, but it's close to 0. And we have a number of observational constraints that tell us that reionization most likely happened between around redshift 6 and around redshift 9-ish. So if you buy Planck, which if you're a betting gambler, Planck is always a good chip to put your bet on. Reionization happened sort of between 7 and 8, redshift 7 and 8. So this means that the first gigayear is just at the end of reionization. So we've gone from early universe physics to just at the tail end of reionization. So in many ways, redshift 5 to 6 is kind of the most interesting point in the universe's history, because in just 1 gig year, we've crammed in all of these things that will only happen once. Now, if you're trying to understand how this happens, whether or not, for example, reionization is driven by AGN, stars in big galaxies, stars in little galaxies, the primary uncertainty for you is going to be how many ionizing photons that are generated by your population 3 and young population 2 stars, your AGN, actually escape the galaxy. Because what's in your ISM? Besides, say, for example, molecular hydrogen, what other kinds of hydrogen do you have in your ISM? Okay, there's kind of like 3 things hydrogen can be: molecular, ionized, and neutral. So the ISM has tons of neutral hydrogen. The ISM is wildly opaque to Lyman continuum photons. So if your ISM doesn't have holes in it, those photons don't get out and you don't reionize the universe. So this is a reionization and escape fractions is an entire industry. You could do your entire career just trying to understand escape fraction of Lyman continuum photons. And because this happens over time, and it's not something that occurs just because the universe is expanding, but because of structure formation in the first galaxies, it's patchy. So in these simulations where the escape fraction is oftentimes an input parameter rather than something that we can pull out, you can see that as you go from the beginning of reionization at redshift 8, this is really the figure you should focus on here, your neutral fraction in the IgM is mostly around 10 to the 0, which is 1, so mostly neutral. Over time, it transitions to being almost exclusively ionized, but you can see as it goes, it starts in bubbles around galaxies. So the physics to think about here is picture a bunch of Stromgen spheres. This is the same physics that drives H2 regions inside of a molecular cloud, just on the scale of galaxies. So each of these patches that are forming here are overlapping Stromgen spheres being driven by the escaping Lyman continuum photons from these galaxies. And this is another thing that's quite interesting. So one of the things talked about here is temperature. The CMB is still hot. So as we go through reionization, we change the temperature of the IgM quite significantly. We go from an IgM that's a few thousand degrees to an IgM that's about 10,000 degrees, because if it was cooler than this, it would recombine. So it's being constantly heated by Lyman continuum UV photons. And so galaxies that are forming after the first billion years are pulling in gas that's around 10,000 Kelvin as its starting point. Whereas galaxies in sort of the first epoch of galaxy formation, they're pulling in much cooler gas that's at lower temperatures, and that is going to make it a little bit easier for them to start to accrete this material. So the first galaxies that are going to start forming around redshift 15 or so don't have to have virial masses quite as high in order to capture and hold on to this gas. So the first halos that are going to form, I'm not going to go into great detail here because Lucio did this really good justice yesterday, are going to be these population 3 forming mini halos. So mini halos around 10 to the 5 to 10 to the 6 solar masses. And this is going to be where our first stars begin to form. So unfortunately, this is one of the places in star formation where we have no local universe analogs. We have local universe analogs for the first galaxies that are primarily forming population 2 stars. Like if you look at the population 2 star formation rate density, even by redshift 15 or so, you're forming an appreciable number of population 2 stars. Those pop3s that form out of truly pristine metal-free gas, we have no pristine metal-free gas in the local universe. And so are uncertainties, you can tell from different models and simulations. The uncertainties on the star formation rate density for population 3 stars are all over the place, like orders of magnitude here. We don't even have a really good understanding of the shape of this because this is purely theory driven at this point. JWST is starting to probe this era, and this uncertainty is going to go down as we start to get more and more observations of galaxies approaching this epoch. Yep.
Can I just quickly clarify on the top 3 star formation rate density plot?
Yep.
The 2 lines from the Park Rig 2022.
Yep.
Total and top 3. So total is all stars?
All stars, yeah. Yeah, so don't compare the dotted line here to the rest of these. All of the solid lines here are pop 3 stars. So the dotted line here is the dotted line on here as well. Yeah. Yeah. Yes. So again, Lucio talked about this. Hopefully you remember everything he talked about because he put a lot of effort into that over years. So I want to do another brainstorm now before we start talking about beating down this uncertainty by actually starting to do observations of galaxies above redshift 5. Yep. Yep. Yes, absolutely, absolutely. I would say that the biggest uncertainty, if the thing you're concerned about is the formation of supermassive black hole seeds, the biggest problem is not that we don't have any theories that work, it's that we have too many theories that work. So direct collapse, supermassive stars, pop-3 mergers, top high of the IMF, these are all things that can plausibly produce supermassive black hole seeds. It's just we're, again, deep in theory land, and we don't yet have good observations to break the degeneracies between some of these theories. So yeah, if for example, nature does produce an IMF for the population 3 stars that is not particularly top-heavy, that's not necessarily a problem for the fact that we see supermassive black holes today. Yeah. So let's get ourselves now out of deep theory land and into reality and start thinking about how we can observe these things. So sadly, I'm going to have to erase our earlier brainstorm. But let's imagine it's 2005. And that might give you a hint as to why I'm picking that time. It's 2005, and you are now on the head of a major grant to decide how to spend money, and you want to start pushing our observations down into the first gig year of galaxy formation. How are you going to find these things? And you don't have infinite time and money. You're going to have to be judicious about yourself. Yeah?
We already mentioned a bit, but like lensing?
Lensing? Okay, so that'll blow up your galaxy in terms of how big it is on the sky. It'll make it brighter. How do you know it's at redshift 6 or higher? Yeah, so lensing is going to be useful and very important for seeing the small scale structures. So that is very deserving to go on the brainstorm board. Yeah? Ah, Lyman break. We're going to be talking a lot about the Lyman break because it turns out that the Lyman break technique, if you're cheap and lazy, which we all should be, it's good to be cheap and lazy, you don't want to waste your money or your time, the Lyman break technique is the easiest way to find a ton of galaxies at a certain redshift very fast. Any other ideas? Quasars, yeah, they're stuff that's far away is going to be dimmer, so if you look for things that are bright, it's going to be easier to find them. So QSOs, the other advantage of QSOs is they often have very strong line emission, which makes it easy to find the redshift. Any other ideas? Yeah? Yeah, Balmer break too. Yeah, so really any spectral breaks. Balmer break has the advantage too that it's not as sensitive to ISM physics because you're looking at the spectra coming off of the photosphere of stars. Any other ideas? Let me seed one. So quasars are a great idea because they're bright. What else could be bright? Yeah, supernova. I'm going to write down a very particular kind of supernova because it's the coolest, weirdest kind of supernova, and it's actually really useful in this case, gamma ray bursts. Gamma ray bursts are bright enough that we might be able to see them out to redshift 20 or so. Yeah? Sorry? Neutrino emission. Oh, from the supernova. That's a good idea. I hadn't thought about that one, actually. I'm not sure how you would figure out the redshift of that, but that might be very interesting. I mean, it's certainly a good thing to be thinking about today in the era of multi-messenger astronomy. Any other ideas? I think we've kind of got a good coverage here of existing and potential future ways to find them. So let's talk a little bit about these. This is great because like I do this and I don't have to have an intro slide because you guys just write my intro slide for me. You guys know so much already. So I want to talk specifically to start about that Lyman break. So for a galaxy at say redshift 7 or so, this is what that galaxy's spectrum is going to look like. You see here the Balmer break. This is caused by opacity in the star's atmosphere, or in the atmosphere of the stars that make up that galaxy. The Lyman break, though, here is just on the edge of that Lyman alpha line at 1216 angstroms, and it's basically everything above the Lyman continuum of 912 angstroms. Why does it exist? We've actually already answered this question. Exactly. And is this neutral hydrogen in the IgM or the ISM? Exactly. If this was in the IgM, it wouldn't help you to find redshift because you would be looking at the Lyman alpha forest of stuff in between you and that galaxy. So because this is in the ISM, the absorption happens in the rest frame. And so Lyman breaks and Balmer breaks are great because you can search for galaxies using dropouts. If you just take photometry using filters, if you, for example, see this galaxy in all of these filters except for the ACS filters here, it drops out, in other words, that gives you a good strong hint that the Lyman break is in between these filters here. So this is what these dropouts look like here. And I like this one from Dunlop's review because it really is perfect for a guy like me who's a theorist because I don't see anything dropping out here. I see a big fuzzy mess. It's this galaxy. But you can see here, this drops out in the ACS-Z filter but is visible in these three WFC3 filters. So this is the cheapest, easiest way to do galaxy hunts at a certain redshift, or really any kind of redshift, because you don't spectroscopy. You can take big images, just use filters, and look for dropouts. The challenge here is where your filter sets live. So if you're looking for the Lyman break at 912 angstroms, at redshift 6, that's 0.8 micrometers, which puts you sort of around here in the HST WFC3 filters. Observations of galaxies above redshift 6 really began in 2009 when this instrument, Wide Field Camera for Surveys, is that what it stands for? Could an observer confirm that for me? Wide Field Camera 3. Oh yeah, I guess 3 is, yeah. But the filter set on this goes fairly deep into the infrared compared to what previously existed on the HST. So that means that you can look at a Lyman break here. These filters will show dropouts. These will not. And the problem is if you go then to redshift 10, that moves you from here to around here. You still have a filter that's finding this galaxy, maybe barely. What's the problem if you only have one filter, though? Contamination's one thing. Let's say you have the most beautiful, perfect image. There's no noise at all. You just have the amount of light coming from a galaxy in one filter. And you want to understand something about that galaxy. Mm-hmm. Yeah. Yeah. Filter. One color.
You have no color, though.
Exactly. You have
One
no
color.
color. That's exactly it. Even though you filter at a certain color, you don't actually have color. You have no idea if you're looking at something that is hot and blue or bright and red. You don't know anything about it except you got a certain number of photons. So you need a number of filters that are further red than the Lyman break. We'll talk about that when we get to the JWST. JWST has a lot of filters that are further red than the HST. The other thing you can do is look for Lyman alpha emission. In really, really starbursty galaxies, like you might expect at high redshift, there's a ton of emission from ionized gas recombining. In fact, this is something that's been predicted since the 60s. I love 60s papers, because can you imagine how much work this figure was to make in 1967? They were probably laying out little symbols and stuff. But that big burst in Lyman alpha emission there can be a useful way to find galaxies at high redshift as well, because this, of course, will be redshifted too. So the idea there is you're looking for a line emission, the Lyman alpha line, and that's coming from the ionized ISM within these galaxies. The other thing you can do is look for dust. So we know that high redshift galaxies tend to be starbursty, they tend to be gas and dust rich. So you can look for them in submillimeter. Here you can see some ALMA observations of galaxies that are invisible in the UV, IR, or visible, I guess, spectrum, but are very, very bright in submillimeter because their dust is emitting a lot of energy. The other thing is that idea that we talked about here with QSOs, gamma ray bursts, violence, big, bright, extreme events. So gamma ray bursts and AGN can be really useful as well because they're bright enough for you to see them. We've got gamma ray bursts now out to redshift 8, but the theory of how bright these things are says that we should probably be able to start seeing them as far back as redshift 20. So what we've seen prior to the JWST, generally speaking, galaxy formation in the first gigayear or so is not all that different after the population 3 era than it is today. It's just slower, and it starts earlier at smaller objects. So this is the number of galaxies you see as a function of their rest UV magnitudes. And if you go back in redshift, you should notice a couple of things. The very bright galaxies are the first ones to drop out. So you don't have very big galaxies early on. And this slope of your Schechter function flattens out a bit here. So the Schechter function is a really important tool in galaxy studies and cosmology. It's basically telling you your number density as a function of mass, luminosity, or magnitude. This is the magnitude form of it. And if you look at the evolution of these constants here, this is kind of your characteristic mass or luminosity at which the Schechter function slope starts to change. Doesn't evolve. This is your normalization. The fact that it's going down with redshift just tells you you have less galaxies at higher redshift, as you might expect. But it's also changing the slope of this power law part. And so not only are you having less galaxies in general, you're having way less of them at the high luminosity end here. So this is telling us that galaxies start forming with the littlest guys first. In terms of the star formation rate density of the universe, I am always shocked by the fact that if you look at the star formation rate density of the universe today, it's around 1/1000th of a solar mass per year, and trace back even pre-JWST, we kind of knew that the universe around redshift 8 to 9 had the same star formation rate density that it does today. But the thing you should know when you look at something like this from 2016 prior to the JWST, these extreme observations with Hubble have huge error bars on them. That is going to be the big thing that we're going to start refining now that JWST is up in the sky, is not only are we going to put some points down on this side of the graph, we're going to shrink these error bars by a lot. So in terms of the observations, how we find these things and what we found prior to JWST, remember Lucio's talk about population 3 star formation. Reionization is done by redshift 6. The first galaxies that are forming are little guys. They're the equivalents of what today would be small bursting dwarfs. And the biggest way that you can get a good sample of these things, maybe not a good sample, but a big sample of these things, is through the Lyman break technique. But you can't do that with HST above redshift 10 or so. So what can you do this with? Obviously, JWST. So JWST, since the get-go, has had a number of deep field observation programs as part of the cycle 1, both the director's discretion and the guaranteed time observation. And the HST filter set can go way deeper. So just to remind you, this is where the Lyman break would be at redshift 10. So this is kind of the end of where you're able to start doing things with Hubble. Well, at redshift 10, you have half a dozen or so filters beyond the Lyman break. So you're actually going to get color for these galaxies. And we are now starting to shrink those error bars and move to higher redshift. So we now have early preliminary work from this excellent review from Harakane looking at things like the star formation rate density of the universe all the way out to redshift 16 or so. Keep in mind, though, the furthest redshift points still have huge, huge error bars. We also have new luminosity functions. And in general, it seems to be doing the same thing as before. We're reducing the number of galaxies and flattening this Schechter function. But the earliest studies, like this, again, this survey from Harakane, are finding actually a surprisingly large number of fairly high luminosity galaxies, much more than previous theoretical estimates predicted. So at that point, really this is kind of uh-oh time. Like, this is not error bars in the sense of, oh, we're off by a little bit. Maybe we're off by a lot. And in fact, maybe we're really, really, really off by a lot. So the earliest high redshift detections around redshift 9 and 7.5, using this Lyman break technique from, I think this was from Sears, from Ivo Labey's paper, was finding galaxies at redshifts with masses so high that they implied star formation efficiencies of 100% or higher. In other words, if this galaxy here has the star formation or the stellar mass that the observations are suggesting at redshift 9.1, one of these galaxies may have more stars than it should have baryons. Which is big uh-oh, big uh-oh. This could mean that cosmology is actually, yep.
I'm just curious why there's no horizontal error bar.
Yeah, me too, me too. Absolutely, that's a very good question why there's no horizontal error bar, because there should be. So this I think is a symptom of exciting science making people run too fast and get sloppy. Because this, Mike's work is great, but the thing is, this was a very fast follow-up to very early preliminary observations. And there was a ton of hype and heat about the fact that the first galaxies that were being detected by JWST at redshift 10 or so break cosmology. But we need to actually think more clearly about how we detect these things. So Sears 1749 was one of these galaxies that will break our cosmology. If there is a galaxy with a stellar mass of 10 to the 9.6 at redshift 17 in the volume that Sears probes, we need to seriously modify how structure formation works. We shouldn't, yep.
So hold on, sorry, I'm just still stuck on the point. So that plot that you showed was actually passed muster with a referee?
Yes, this is in
Okay,
nature
that's fine.
astronomy.
Nature.
Nature astronomy, yeah.
That explains it.
I mean, you know what they say. Just because it's published in Nature doesn't mean it's wrong.
Sorry, but these 2 points do not come from the paper.
Well, no,
Is it reporting?
Yeah.
Someone else?
Yes, so really, if you're going to blame anyone, blame Labe. But you shouldn't blame anyone. This is not bad science. Interpreting it as a catastrophe for cosmology is bad science, because if you take a look at how we do these Lyman break detections, we use filters where we don't detect the galaxy, and filters we do detect the galaxy, and SED fitting models for the spectral energy distribution of the galaxy to predict how much flux we should get in those filters, and then we do fancy statistics with our SED fitting tool to figure out what redshift this has to be at to put the Lyman break at the right frequency. Well, the thing is, there are many different SEDs you can get. So Sears 1749, which is one of the galaxies that would really break cosmology, is actually at redshift 5. It's not at redshift 16, it's at redshift 5, because if you model a very dusty starbursting SED, you can also fit this, and follow-ups that have done spectroscopy where you're not just looking at individual filters, you're looking at this full spectrum, confirm this. The other thing is the mass. So the error bars on the redshift should be huge. The error bars on the masses should also be huge. You can take simulations and do mock observations of them. The simulations might be wrong, but your tools for observing them should still tell you what's going on in those simulations. And if you have a burst of star formation near the redshift you're observing, you can get stellar mass estimates by fitting that SED that are off by an order of magnitude or so. So there should be order of magnitude or so error bars on many of these mass estimates, and difficult to estimate error bars on the redshifts as well. So what we really need is spectroscopy, and unfortunately spectroscopy is expensive and hard to do. We have now spectra of some of the highest redshift galaxies out there. I believe GSZ13 is still the record holder for the highest redshift spectroscopically confirmed galaxy. But when you start doing this, you can see that you were getting some bias here. Some of them were very embarrassingly bad. This point here on this plot, hurts every time I've seen it. But Harakane's just gone and done a follow-up now. It's on the archive. The same analysis restricted to galaxies with spectroscopically confirmed redshifts. And when you do that with the spectroscopically confirmed redshifts, you do get occasionally some galaxies that have higher star formation efficiencies than semi-analytic models predict, but you're nowhere deep into this regime where you're prohibited by lambda CDM. And the simulations actually confirm this. We've had simulations for almost a decade or more now that have data at redshift 10. We run cosmological simulations typically starting at redshift 100 or so. We just have never thought to actually look at much of this data because there's no observations to compare to. And so all of the major simulation projects, large volumes, have galaxies around the same mass that are being seen by JWST at redshifts of 10 to 13 or so. And if you take a look at their properties, like their star formation rates, they're again just more or less in line with what's actually being observed here. And these simulations are big volumes, so you're probably thinking, well, the resolution there isn't very good. These are galaxies, if we go back here, these are probably galaxies that maybe have 1,000 star particles in them or so, probably less. So what about higher resolution simulations? Well, they also are agreeing more or less with the spectroscopically confirmed properties of high redshift galaxies. So the blue points here, or the blue hexes, are from my analysis of those lower redshift volume or lower resolution volumes. The orange points here are from very high resolution, like 1 parsec simulations of reionization from John Wise's group. And there doesn't seem to be that much of a problem for our theories for galaxy formation based on the spectroscopically confirmed data from the JWST. So, catastrophe averted? Maybe. Hopefully there's another catastrophe in the future, because that's fun and that's what makes science exciting to do. But I think this is where I want to leave you. I'm starting from the bottom. Lambda CDM is still alive for now. JWST hasn't broken it badly. The thing is, JWST is an amazing instrument that we don't yet fully understand how to use to its full potential. Interpreting data coming out of, oh, Amy, I see you shaking your head. Do you disagree with me?
I do. I think that getting photometry from JWST is basically robust, especially in a basically empty cosmological field. The problem seems to me, having not read the paper, was that they did a not excellent job on the stellar population synthesis fitting of, so, and that technique is old. So they don't get to wiggle out with some excuse like, oh, JWST's new, in my opinion.
I'm trying to be nice.
And that's to your credit, but you know, we're at a school and I feel that if someone's gonna be an asshole, I'll do it. And I'll just say they don't get to wiggle out, so I don't agree, but anyway.
Well, I'm glad that you, honestly, I think it's better that you say that, because you are better, you understand the field of observing better than I do. So what seems like
I've done stellar population synthesis fitting of galaxies that Z of eons ago used to be high 3. Mm-hmm. And as a master's student, I could put a decent error bar on that.
Okay, well, then there's a lesson for all the students in the room, is don't be sloppy. Your takeaway on that, don't be sloppy? Yeah, I mean, who knows? It may have been a rush, because first, there's always rewards for getting a first. But the thing is, I think this speaks to what you said. It's challenging, but it's not insurmountable. And we've been detecting galaxies at redshift 6 or so for 10 years. This is not something that only just yesterday became available to us. We can constrain some cosmology using early galaxies, but so far it seems like the constraints from galaxies are weaker than the constraints from Planck, and they're more or less in agreement with each other. And finally, galaxy formation post-reionization is basically the same physics that you all know and love for regular galaxy formation. It's just more so, more mergers, more gas accretion, more starbursts. There isn't really very many mechanisms, unlike with population 3 stars, where totally different physics is involved. Okay, all right. Well, I think we have maybe a little bit of time for questions before coffee. Cool.
Just some comments about, it's true that we are detecting galaxy about redshift 6 already with HST, but it's important to notice that now we are looking at their physical properties, because as you said, there was only one filter, so the only thing we did is luminosity function in the UV, right?
Yeah, yeah.
Go.
Yeah, I mean, that is one of the huge powers now, is that we're not just doing brightnesses. We have things like, I touched on it briefly, reasonable estimates for star formation rates, sizes, metallicities. And again, I think one of the unfortunate things about this early sloppiness was most of what people were talking about were the cosmology implications, which turned out to be none. There are no cosmology implications, because the ones that are a problem are misdetections.
Not yet.
Not yet. Yeah. But the thing is, there is incredible good work that's going to be done over the next 5 to 10 years in terms of things that we used to only be able to do at low redshift, like size-mass relationships, mass-metallicity relationships, at redshift 10. And again, it may not be a problem for Lambda CDM, but I strongly suspect it will be a problem for our galaxy simulations. And that's going to be very exciting.
Yeah, yeah. And the other thing is about the luminosity function, because so it's true that in your
here
analysis,
I can go back.
that plot.
So this isn't a luminosity
no, the
function.
One, the one
here.
No,
No.
You showed your data, your simulation that you find. You can recover them in simulations, essentially.
Sorry. Yeah, that is later.
Yeah, this one.
The star formation, the SFR stellar mass relationship. Yeah.
Yeah, but so what is coming now, because more and more spectroscopy is coming out, so you see that when you look at the volume density, the number of galaxies in volume density from redshift 13 down to 9, it doesn't change very much the numbers. So essentially the galaxies have the same luminosities, then the star formation efficiency has to be higher, which in turn will mean that the star formation red density per moving volume goes up. It doesn't go down anymore. I think that's the only things that was not predicted before, right?
Yeah.
And has changed. It's not cosmological, but in a sense it's telling us the galaxies are producing more stars at the very high redshift than we thought before.
Yeah. Right? And that's an interesting one, because those are two things that is a rock and a hard place, because you have a pretty decent constraints on when reionization has to happen. And if you know, let's say we knew the exactly what the star formation volume density of the universe was to redshift 30. If we knew that exactly, and we know when reionization happened, then we know the escape fraction, or at least some integrated averaged version of it. Yeah.
One more question? Or coffee? It's looking like coffee to me. One tiny public service announcement for the women that used the bathroom right here, the stall on the right. Careful with the lock, that you don't get locked in. It almost happened during this session to me.
Bathroom of Amontillado.
Let's thank both our speakers again. And we'll come back at 5 after the hour.
Hey, I did have a quick question that is tangential, but
So if you use the number counts that you see at redshift 10 to kind of trace back what the star formation history was at redshift 20 or so, that's one of the big inputs for predicting when reionization happened.
Right.
Yeah, and so like the closer you can get to when reionization happened, the less uncertainty you have extrapolating into the past.
Absolutely.
Yeah.
Yeah, my experience is strictly in reconstructed star formation histories from deep CMDs.
Okay.
Of dwarf galaxies, so looking for like how reionization can impact dwarf galaxies at different mass scales.
Cool.
Yeah. So it's
I mean, that's the thing. Dwarfs are local universe analogs for all of this stuff. Like, if you want to understand it, you can fight at the high redshift universe, or you can kind of try and extrapolate what you can from like low metallicity dwarfs in the nearby universe. Yep. Cool. You're welcome. Good luck. see that. Thank you very much, University of Memphis. Oh my God. Well, this might be a short talk. Uh-oh. Does someone have a computer I can borrow with PowerPoint on it? Thank you. I'm so sorry. I will email you my slides right now. And, geez, sorry about this, folks.
How often does that happen?
It's never happened before. I didn't know that was a thing that could happen.
This is good to know.
Yeah.
Are we doing okay?
Yeah, we might be a few minutes late.
Take your time. We still got 5 minutes. Well, no, we don't, but it doesn't matter.
Oh my God, and now it's stolen my mouse. Yes, I know.
Pure panic now.
Yeah, this is pure panic mode. Okay, I'll use my phone.
This is my email. It's over there.
Thank you. Oh, this is embarrassing.
That's why I use Windows. I might be still like the weird one.
No. Yeah, I'm normally like, if it's my work, I'm fine, because like I need it on my laptop, but I'm working with Dietrich's slides, and so I needed PowerPoint. Okay, let's see if I can get this working.
So in the last session, I failed at correctly naming out chocolates, and there was a lot of participation. So if anybody wants, there's a couple different varieties of things here. Just come and get them, or whatever you want. But there's more. Can you look around until I type in?
Yeah, here, do you mind if I get my slides fixed before I put that on? I'm just having a problem with my slides. Do you mind if I get that fixed before I throw on the mic? Just in case we're talking back and forth. Thank you, sorry. Okay. Here we are, okay. Set everything up. I think you're fine. Thank you. You're a lifesaver. Yeah, that's good. I need more stickers. Okay, well now you have my slides too. Oh, you know what? I'm going to put a sharing link in this Slack. Let's see if that works. Oh, I'm going to use Flo's computer. Yeah. Oh, thank you. Yeah, it'll just download, I'm sure. There's always got to be one talk, and sadly this time it's me. Oh my God, it's the permissions. Okay, give me a sec. Oh, okay. Okay, I'm going to send you a new link. Let's try new link. Let's see if that works. Okay, thank goodness. All right. And I think probably you'll just have to download it. Yeah. Yeah. I think if you just go save as. Oh, actually, it might work in. Might work in. Yeah, that's the problem. Try reloading the. Yeah. I owe you. I owe you big time. Okay. I think we're good now. We're good now. Yeah. Yeah. Cool. Yeah. Yeah, I should be fine. All right. Sorry about the delay, folks. Blame Bill Gates. Okay, so shall we start now? Excellent, excellent. So I'm going to talk now to folks about globular cluster formation, which is again kind of a, we think, a high redshift phenomena. Forgive me, I'm not Diederik Krausen, who originally gave this talk, and these are his slides. Thank him. Just imagine me being a little bit taller, a little bit blonder, and a lot skinnier, and it should be the same experience. So yeah, I'm going to talk about how these dense, old, metal-poor star clusters form, and I really want to talk about the environment in which they form, because we know already from all of the talks we've seen thus far that star formation at high redshift, especially around cosmic noon, redshift 2 or so, was intense. Star formation was most intense at cosmic noon. In fact, we're kind of in the tail end of the universe's history. Things are boring from here on out. But we do see in the nearby universe places where star formation is proceeding intensely, namely in starburst galaxies. And especially when we zoom into these kinds of objects, we can see these young, massive clusters. Some of them are big enough and compact enough that we think that they may be long-lived, that they're not just going to evaporate as they lose their gas. And so we might ask, looking at these things in the nearby universe, if we think some of them may be long-lived, maybe some of them have survived from the early universe. And anytime you see a question in a talk, if it's a question that's like, ooh, that would be exciting if it's true, the answer is normally yes. So I'm going to argue on Diederik's behalf that what we see as globular clusters today are the high redshift analogs of the young massive clusters we see in the nearby universe. So we kind of have to start out with that boring task that we often start out with of things like definitions. So we want to define what are the physics we care about. In other words, what are the important physical mechanisms that shape the population of globular clusters we see today? And can we use globular clusters clusters of stars that are old, with ages of around 10 gig years or so, massive, 10 to the 4 to 10 to the 6 solar masses. They tend to live in galaxy halos, so they don't share the same spatial distribution as the rest of the stars, and especially the young stars within the galaxy. They're metal poor, which you might infer from the fact that they're old. The universe itself was metal poor 10 giga-years ago. And if you look at the color magnitude diagrams of the stars within these globular clusters, they host multiple populations, which in other words means that they have populations of stars that have different metallicities. These don't all have the same metallicity, which implies some weird stuff about their formation. The problem with a quantitative definition like this is we have exceptions to all 5 of these things. There are younger clusters, smaller and more massive clusters, clusters in the disk, relatively metal-rich globular clusters, and globular clusters without multiple populations. And so we kind of have to work within these definitions but not be bound by them. So let's go back to the beginning now and ask ourselves, how do these things form? And when I say go back to the beginning, I don't just mean go back to the beginning of the redshift at which these formed, potentially 10 giga-years or so ago. Let's start with a smaller jump. Let's go back 50 years to the earliest ideas about how these globular clusters form. And so for the past 50 years, globular clusters are easy to detect. These are not new objects that we've just discovered. We've known about them for as long as modern astronomy has existed. And so theorists have pulled ideas out of somewhere for the last 50 years to try and explain how you get these unusual, dense, old star clusters. And every decade or so, a new idea comes along. So one of the earliest ideas was that at high redshift, you have a thermal instability and you basically collapse a chunk of gas directly into a globular cluster. As the HST started revealing these young massive clusters inside of merging galaxies, it was a very exciting result because a lot of people cued on to the fact that these things are about the same masses as globular clusters. We've had some ideas involving cosmological formation, so basically these things form before reionization in dark matter mini-halos, or perhaps they're the result of another kind of galaxy interaction. They're the stripped nuclei of dwarfs. So the problem with all of these is they all have issues explaining the populations we see. So these high mass, or these thermal instabilities at ultra-high redshift can't work because this involves instabilities around galaxies. And low-mass galaxies that have never had one of these hot circumgalactic media still have globulars. So if you form these things in the hot gas around galaxies, you would not expect to see them in galaxies that have never had hot gas surrounding them. In major mergers, we might predict that some of these things come from major mergers, but there are low-mass galaxies that also have globular clusters that we can infer that they most likely have never had a major gas-rich merger. So if this is the only mechanism, these galaxies also shouldn't have globular clusters. We probably don't form these globular clusters in their own dark matter halos because they would retain some of that dark matter, and we could detect it kinematically in the outskirts of these globulars. And if they were the nuclei of dwarf galaxies, we would expect them not to have multiple populations, but an entire spread of iron abundances. And on top of that, if you look back at what you think, say, for example, the Milky Way's merger history is like, we simply don't accrete enough dwarf galaxies with these massive nuclei to explain the number of globulars we see in the Milky Way. So most of these early universe exotic physics mechanisms have major problems explaining the populations of globular clusters that we see. So we might be screwed as theorists. Because it could be that what's actually going on is some mix of all of these and other things that we don't understand. But we might actually not be as screwed as we think, because if we look back at when globular clusters form, their typical formation redshift is about redshift 3, very close to cosmic noon, when the universe is the most efficient at forming stars. Three-ish star formation. So we've seen a couple of talks already. Miroslava's talk, especially yesterday, was phenomenal, looking at how much we now know about the way that star formation progresses in these very gas-rich, very clumpy galaxies from redshift 1 to about 3. And the feature that these galaxies have that is different than present-day star formation is that the gas pressures are significantly higher. 10 to the 7 Kelvin per cubic centimeter, compared to the Milky Way, which is 3 orders of magnitude lower for the average ISM, although this is kind of comparable to the central molecular zone. So if this is the case, then we can kind of understand how globular clusters form as a process of normal star formation at high redshift, combined with the evolutionary pressures that take place as globular clusters live for the remaining 10 gig years that get them to today. And if you look at young massive clusters in low redshift analogs of these gas-rich clumpy disks, these YMCs have similar properties. They're similar in size, a few parsecs across, similar in mass, around 1 million solar masses. The only difference is these things are forming now, so obviously their ages are different, and they're forming out of much more gas, or much more metal-enriched gas, so their metallicities are much higher. So Occam's razor, as Diederik would like to say, suggests that we already have a mechanism that we can see today in normal, nearby physics that can explain globular cluster formation. So in galaxies in the nearby universe where gas pressures are high, the star formation rates are also concomitantly high, and we see globular-like clusters, they're just young and metal-rich, forming in these environments. We also know that this kind of environment of high gas pressure and star formation rate is what all galaxies that were vigorously forming stars that gave us that peak of star formation at cosmic noon looked like. So, question we can ask with this is, are these globular clusters just the high redshift analog of normal young massive star cluster formation today? And to know that, we have to know, can these things survive to the present day? And if they do survive to the present day, are they consistent with these properties I brought up at the beginning? Are they metal poor? Are they massive? Do they have multiple populations? So what we need to do to understand this is really not just understand formation of globular clusters, but their evolution too. Because you may form globular clusters that don't match reality, but if you destroy them by the time you get to redshift 0, you might be fine. So what this process of trying to understand our globular cluster populations today really looks like is a process that starts with us understanding how clusters form, which really means understanding how stars form, understanding how clusters disrupt. So we've already seen there's multiple mechanisms that can remove mass from stellar clusters. And then also understand how the galaxy evolves, because even if you form a globular cluster as a theory problem, a painfully multi-scale process. We have to understand our cosmological structure. We have to understand how individual galaxies form. We have to understand how stars within those galaxies form. And then we also have to understand clusters themselves that have formed out of that gas, how they lose mass due to things like evaporation, tidal interactions, stellar evolution, to eventually give you a cluster that ends up back in your big galaxy situation. So this is painfully difficult. And before we dive into something painfully difficult, I threw in my own slide. I'm not just aping Diederik. I want to have another discussion because these are fun. So I'm once again going to poll the audience for some ideas here about this problem of developing a theory of globular cluster formation. So I've got some suggested questions up here on the board. If you've got an idea as to either a relevant thing or an answer to one of these questions, throw it out there and I'll put it up on the board. Doesn't have to be these questions too, if you've got your own ideas independent of this. Yep. Mm-hmm. Okay, so that's two things. Form even earlier, which maybe that could be fine for this definition of 10 gig years or so. Like in terms of time, redshift 3 isn't that much different than redshift 7. But also, when you say forming around halos, do you mean like in the outskirts of galaxies?
Yeah, so we have some small dark matter halos around the outskirts of our galaxy as well. So they're kind of just blobs of dark matter.
Okay, so substructure.
Substructure, that's probably the best word for it. And around those, and it's very similar to, there is a new formation, supersonic.
Oh, SIGOs.
That one.
Supersonically induced gravitational objects. This is another new exotic mechanism for forming globular clusters. Basically, it's shock waves in the intergalactic medium. Yeah. Yeah. Mm-hmm. Mm-hmm. Yeah.
I mean, this doesn't mean the star cluster couldn't form earlier.
Yeah, absolutely. Well, there's kind of two things. Like, it would be wonderful to just understand cluster formation in general at high redshift, but that wouldn't totally answer the question as to where the Milky Way or any other low redshift objects, globular clusters, came from, because of all of the various disruption mechanisms that are involved. So, like, I guess it is kind of like I said, three problems. There's high redshift cluster formation, the various mass loss mechanisms, and redistribution, all of which are important questions. Not saying that one is the
Maybe a bit basic for the disruption, but just the n-body dynamics of the stars.
Yeah, in fact, almost all of the disruption mechanisms that are important are n-body dynamics effects. So you kind of nailed it in one two-word phrase. Yeah.
So for the formation of the globular clusters, so we need to make a kind of clump with high pressures, as you mentioned, in the first place. So we need to think about like what components can be contribute to that high pressures, like turbulence or gravity, maybe cooling.
That's a very, very good point. How do you make a big clump? Yeah, because it's one thing to say, okay, clumps come from somewhere and then they form stars. But if you don't know where the clumps come from, you kind of don't understand where the stars come from either. Any other last ones before we jump into the next part? Yeah?
Sorry, I mean, the testing of the ideas for the n-body dynamics, we have n-body codes to simulate that.
So that's a good idea. And in fact, I'm gonna expand on that and say simulations. Because one way that you can test some of these ideas is model it in a simulation and see if the globular cluster population that comes out looks anything like what we see in nature. So if you can capture your idea as a model and run it as a simulation, barring all of the various uncertainties that always come along with simulations, it's a way of disproving models, which should be all of our bread and butter. So I'm going to talk now a little bit about some of these ideas, and hopefully I'll do them justice. So really what we're talking about here is kind of a two-phase model for cluster formation. We start with young massive clusters in a gas-rich disk, and in this gas-rich disk, one of the big pieces of that n-body dynamics that can disrupt clusters is tidal shocks. So tidal shock interactions with other molecular clouds within the disk. So a cluster passes by or through a cloud, and the gravitational torques involved in that dynamically heat the cloud, cause it to lose stars. But we know that these galaxies at redshift 2, not only are they vigorous star formers, they're vigorous mergers. There's mergers all over the place at redshift 2. And if you've ever looked at a merger, you see that you get tidal tails. And so these mergers can cause globular clusters to migrate away from the gas-rich disk, where disruption is very, very efficient, into the outskirts and potentially even out into the halo, where there are no big, dense things. The halo we know is gas poor compared to the ISM. And they're now going to be in this mode where they're slowly evaporating. So one of the most fun things you can do in a StatMech class is calculate that self-gravitating systems have a negative specific heat capacity, and therefore you have this idea that the core of a globular cluster will contract over time and shed its angular momentum into its outer stars, which will evaporate. And this process is very slow. So really, we've got two ways of disrupting globular clusters here. One where these clusters are still young and living in the disk, and a second one that's kind of slow and steady once they've been kicked into the halo. So each of these parts has been studied in different techniques, observationally and through simulations. But it's very hard to tie all of these together in one kind of complete theoretical model. So with simulations of young massive cluster formation, you have the advantage that you're simulating a small object, a single molecular cloud, which is tiny compared to cosmological scales, big compared to me. And so you can actually resolve individual stars, and you can do things like directly resolve tidal disruption. It's not something you need to model. as long as you're modeling gravity correctly. You can model this migration by, of course, throwing globular cluster particles into your galaxy and seeing how those globular cluster particles are ejected. And of course, you can do things with both semi-analytic and hydrodynamical methods, but you're not resolving that YMC, you're not resolving the individual stars, and so you have to have some subgrid model for the cluster particles, how they form and how they evolve over time. And finally, like if you want to study how these things evolve in halos, you really need like a full N-body simulation where you can generate these beautiful little tidal tails from the merger debris of past merger events. So to get this right in your model, you need all of these ingredients. You need the formation, you need the rapid disruption, and you need the slow disruption that's triggered by moving these globular clusters out into the halo. And the fact of the matter is, one is not possible. We cannot simulate an entire galaxy to redshift 0 at the resolution of individual stars. We have to use two instead. Make assumptions about the missing steps. So we can't get everything right, obviously. There's no such thing as a free lunch. But if we put these pieces together rather than simply studying them independently, we might be able to build up our physical understanding of this process and push towards a better answer and perhaps one day a complete model. So what are the various physical mechanisms that are going to be involved here? So I mentioned them kind of briefly here. And what we're going to do, what I'm going to talk about for the rest of this talk, is an attempt to put all of these physical mechanisms together in an end-to-end model. So this is the eMosaics project, and what it is it's a galaxy formation project making Milky Way-like galaxies using the same well-tested galaxy formation physics from the Eagle simulation, but with models that make assumptions about those missing steps for each stage of the process, from formation, rapid disruption, to slow disruption. So what you see in this model, or in this video from the simulation, are star particles that have been tagged to contain globular clusters, colored by their mass. And it's hard to watch any individual particle here, but you can see actually that some of these colors change over time as these globular clusters lose material. So this is the first time that this has ever been, yep?
So each point is like 10 to the 6 stars or something like this?
Anywhere from 10 to the 3, I think, up to about 10 to the 6. Okay. Yeah, yeah. So this doesn't defeat the purpose of any of those other simulations, which each fit into a particular niche. But this is the first time all of those pieces of physics were put together in one kind of end-to-end model. And so the first part of that model is the formation part. And so we numericists call ourselves theorists, but really in many ways we're oftentimes theory users rather than just theorists. So we develop theories like, for example, a cluster formation theory that's based on observations of young massive clusters. If you look at the cluster formation efficiency, which you measure through observational magic, as a function of ISM gas pressure, which you also measure through observational magic, you can reasonably well fit this with a single analytic function that is just a function of either gas surface density or gas mid-plane pressure. So the higher the surface density or pressure, the higher your cluster formation efficiency. So this is the model, this is the observations. And you can see it does reasonably well here. So here we're comparing about against star formation surface density, which, if you believe the Kennicutt-Schmidt law, traces the gas surface density to the 1.4 power. So you transform this to the 1.4 power, and you match the cluster formation efficiency in nearby galaxies reasonably well. So when we plug this into our simulations of Milky Way-like galaxies forming over cosmic time, what we see in terms of when these clusters are formed is that they peak in their formation rate around cosmic noon. That's so far so good. That's one piece of the puzzle that needs to be done right in order to get a globular cluster population like the one we see in the Milky Way. We need a cluster formation efficiency that's high at high redshift and low today. And this is all just a consequence of the fact that gas pressures and gas surface densities were higher at higher redshift. And because the gas in the galaxy is being enriched by populations of stars that subsequently form. When you're forming clusters at redshift 2 or 3, you're forming them out of lower metallicity gas. So the young clusters that are forming near redshift 0, of course, have metallicities near solar. So this next piece of the puzzle is, okay, we know how efficiently we want to form clusters, but how do you decide what kind of cluster you form? Do you form a big cluster or do you form a little cluster? So the so-called salpeter slope we think is probably important not just for setting the IMF, but also the initial cluster mass function. So all of the physics involved that might give us an IMF should give us an IMF-like function for clusters called the initial cluster mass function. And just like with stars, where we have physics that sets a high and low mass limit, for stars, the 0th order approximation is the Eddington limit. For globular clusters, we have limits in terms of gravity, shear, and feedback. So you can't build a globular cluster bigger than the maximum mass of a molecular cloud that you can form in your galaxy. And the maximum mass of that molecular cloud you can form in your galaxy is set by the Toomre limit. So here is what we get in terms of observations of the cluster mass function for young massive clusters in nearby galaxies. So you can see it kind of looks a little bit like an initial mass function for stars. Okay, so we've got how efficiently these form. We've got a mechanism for setting how massive they are. Now we need to start thinking about what happens after they form. So how do we start evolving these things, moving them around, removing mass from them, etc. So we have to think about disruption. So the simplest form of disruption is this classical two-body relaxation. So even a globular cluster sitting in an empty universe will eventually lose mass because its core will contract and it will shed stars from the outside. If you split this into two things, the core is hot, the outside is cold, and because this thing has a negative specific heat capacity, heat flows in the opposite direction you would expect it to. But the problem with trying to explain all of globular cluster evolution based only on this classical evaporation is that it's very slow. And if it's the only disruption model or mechanism you have, it gives you things like a characteristic globular cluster mass that's lower as you get further out from the galaxy, which is the opposite of what we see. So there has to be something beyond this. We can't throw this away because this is like, in terms of physics that you can trust, just classical Newtonian gravity is physics you can trust. So it's got to be there, but it can't be the only picture. Perhaps the other mechanism that can give you fast disruption is tidal shocks. So something like this schematic movie you see here, you move a little diffuse object like a molecular cloud past a globular cluster, and the tidal impact of that, let me play that movie again, the tidal impact of that heats up the globular. So you can see after the thing has passed, this cluster is losing material much more quickly than it would have otherwise if it hadn't had this tidal interaction. And so the source of these tidal perturbers in a real star-forming disk is going to be all of that gas that you're forming your clusters out of. You are forming clusters out of these very large, massive molecular complexes. And once you form one of them, all of the other molecular clouds there are still kicking around ready to do violence to your young new cluster. So the problem with modeling this, if you say, for example, want to simply tag stars that have already existed in your simulation rather than including a model in the simulation, is these tidal heating events happen over very, very short time scales compared to the typical time scales over which you output snapshots from your simulation. So if you zoom in here, we've got 3 clusters here, 2 of which are still alive at redshift 0, one of which has lost all of its mass. And so if you go back to redshift 3, around where these things form, you can see that the ones that survive spend most of their time at low tidal heating rates. One of them spends its entire life at low tidal heating rates because it formed in the outskirts of the galaxy. Another one forms in the inner parts of the galaxy, but during a merger is kicked into the outer parts where it no longer encounters these tidal perturbations from clouds within the simulation. But for the one that's disrupted, it's disrupted fairly quickly. And if we zoom in here on this panel, you can see that we're getting orders of magnitude fluctuations in the tidal heating rate on timescales of 50, actually more like timescales of 1 to 10 megayears or so. So this means you really want to include this disruption mechanism as a part of the simulation itself rather than some sort of post-processing that you would do afterwards. And so these mergers that you get at high redshift are really one of the key pieces to allowing these clusters to survive. If this globular cluster had not been ejected, it would have evaporated its entire mass before redshift 0. Okay, so let's recap on the mechanisms that are involved here. So we've had 50 years or so of trying to explain globular cluster formation purely through exotic early universe stuff. The problem with many of these things is no single exotic early universe mechanism can explain the populations of globular clusters we see today. In terms of developing a model based on something a little more mundane, normal star formation at high redshift, actually getting the predictions out of that is difficult because all of these approaches have limitations to them. And so you really need basically a whole community working on this. But so far, the kind of, I would say, somewhat controversial, but not hugely controversial picture we have of globular cluster formation is that these things are forming in high redshift galaxies because high redshift galaxies are rich in gas, high pressure environments where cluster formation is high, and because they are also environments where mergers are frequent, the fact that they have high gas fractions doesn't necessarily mean all of those clusters will be disrupted. Some can be ejected from this kind of violent birthplace. So I want to talk now about the results of these simulations. So the original eMosaic simulations are a set of 25 Milky Way-like zooms. So this is an attempt to understand the population of globular clusters in Milky Way-like simulations, or in Milky Way-like galaxies. Now, these aren't the only simulations we ran. We actually ran hundreds of these because what we wanted to do was test different physical ingredients. There are uncertainties in each of these pieces of the puzzle. There is uncertainties in the formation model and uncertainties in the disruption model. And there's no way to understand different potential pieces of the puzzle are correct unless we see what they produce. So currently there's a big volume being run, but I don't think that there's any major results out of that yet. So what the main results of eMosaics are what I've already told you. Globular clusters are the natural outcome of kind of normal cluster formation at high redshift. Now, we know that because these slides were made after the eMosaics results were starting to be analyzed, so we put that in the introduction. The other thing that's very interesting is it actually does a good job of reproducing the young cluster populations. Of the cluster formation efficiencies, their masses, and age distributions, it's doing pretty well in terms of the young young cluster formation as well as globulars. It reproduces some of the globular cluster population properties, but not all of them. So it gets the number of globulars per unit galaxy mass correct. So there's a very shockingly tight scaling relationship between the halo mass of a galaxy and the number of globular clusters it contains. The density profiles and kinematics, the ages and metallicity distributions, the high mass end of the globular cluster mass function, so you can probably guess the low mass end we're not doing well on. As well as globulars in kind of exotic environments like stellar streams, as well as how many stars in the halo and the actually our former globular cluster residents. So the thing I worked on in the eMosaics project was basically tracing back the globular clusters that we see today to where they formed and what was going on within these galaxies. And so here you can see a galaxy that is at redshift, I believe this snapshot was a 2.3, so around cosmic noon. And I've tagged clusters that have now formed that will eventually be haloglobular clusters in the Milky Way thing that this turns into at redshift 0. And you can tag them based on how their gas got into the galaxy. So you can see that here we've got a number of these things, in fact the majority of these things, that never went through a shock heating event. They were accreted either onto the main halo or these satellites through cold accretion. And you also see that we have some of these galaxies marked with squares, some of them marked with dots. The ones marked with squares are ex situ globular clusters. These were formed in other galaxies that were accreted by the main halo, and they brought their globular clusters with them. So this is just one example, but we've got 25 galaxies with 100 or so globular clusters. In each of them, we can do some statistics on this. So what we found from this project was that the vast majority, about 2/3 of globular clusters, don't actually have to be formed in either major or merger events. They can form perhaps after, perhaps before a merger event, just from the gas-rich clumpy disk that's sitting there vigorously forming stars at redshift 2 to 3 or so. So the majority of these things come from gas that was accreted cold onto the galaxy smoothly from filaments rather than from other dwarf galaxies bringing things in. Only about 15 to 20% of the globulars in the Milky Way we predict come from mergers. And because of that, about 2/3 of the globular clusters in the Milky Way are in situ. Now you might be thinking, how can the ex situ fraction be higher than the fraction that formed during mergers? These are different things that we're talking about here. Globular clusters that form during mergers are clusters that form in some galaxy that is currently undergoing a merger. Now that galaxy might be the main progenitor of the Milky Way-like galaxy, or it might be a satellite. So a globular cluster that doesn't form in a merger can still be ex situ if it forms in a clumpy, vigorously star-forming galaxy, and then later on that galaxy merges with the Milky Way. So we predict as well that about 2/3 of the globular clusters in the Milky Way are actually formed in the main progenitor of the Milky Way halo. The other thing that's very cool about this, that's really starting to become kind of urgent, is we're starting to get protoglobular clusters with JWST. We've seen today and yesterday a bunch of really, really cool results of what I don't know, am I being too optimistic to say what are probably the protoglobular clusters in these galaxies at redshift 2 and 3? Angela, am I being too optimistic? Would you say that we're starting to see protoglobular clusters now, or that we're on the cusp?
No, I think they are genuine proto-GC candidates. It's difficult, right?
Yeah.
You show it's difficult to predict
Yeah.
what is going to happen.
Yeah, they may not be surviving to redshift 0, but they're definitely the kinds of things that if they had the right environment could.
Yeah, exactly. And they were.
Yeah, yeah.
So in a sense, you are looking at the one that
Survived. So, yeah, I should have probably added more slides about my own paper from this, but this paper, one of the things we do is we do that side-to-side comparison. We have the same analysis done for the ones that don't survive.
Yeah, exactly.
Yeah.
So in a sense, it's not that they cannot form a ratio 10. It's just
Yeah.
that they do not
Survived. Exactly, exactly. Yeah.
So that's the
Yeah. And one of the big results there is there actually, at least in this breakdown of origins, there's not a huge difference in survival in terms of like where they formed. So if you form, say, in a minor merger, that doesn't really impact whether or not you're going to survive to redshift 0. So one of the other things that you can do with this is make predictions for how many protoglobular clusters we're going to detect. And so this is very relevant to what this conversation we're having, is survival is important here. Unlike the galaxy luminosity function, which is increasing in volume density as you go to redshift 0, for clusters that are about the same mass as globular clusters, protoglobular clusters, the luminosity function, or in this case it's a number density function, is actually going down over time. And that's because of two effects. That's because the galaxies that are forming stars at redshift 0 tend to be much more like the Milky Way, with low pressures, relatively low star formation rates, and relatively smooth ISM. At higher redshift, clumpy, gas-rich, high-pressure disks are ubiquitous. So you're forming a ton of these things, and because unlike a galaxy, there's no way to unmake a galaxy, as these things die off, you end up having less globular-like clusters at redshift 0 than you did at redshift 1 or 2. So really it seems like if you're a globular cluster, redshift like 1 is the best time to be alive. One thing, though, that we don't do well is the low mass end of the globular cluster population. So in eMosaics here, this is the distribution of cluster masses as a function of mass. So you can see, compared to the Milky Way, we are off for low mass, 10 to the 4 or lower solar mass clusters. We're off by more than an order of magnitude. And this is what I mentioned before about falsifying hypotheses, because this is really cool. This is honestly, in my opinion, one of the most important results we have. It tells us something about the physics. And what it tells us about the physics is that we're missing something. So because the eMosaics simulations were run with the EAGLE model, which uses a very smooth cooling, how do I phrase this in a way that isn't too technical? Basically, they enforce their ISM to be gene stable at relatively low densities because of numerical resolution issues. They don't actually, we didn't, in the eMosaics simulations, get to be able to form particularly compact or dense molecular clouds. So that formation, or that disruption mechanism of tidal interactions was inefficient because we didn't have enough lumpy pieces of the ISM. So a new simulation building off of this called EMP Pathfinder that was really spearheaded by Marta Reina Campos. This is really like an unbelievably ambitious PhD project. I can't believe she managed to pull it off during a PhD. Completely rebuilt the galaxy formation physics that was used in EAGLE to better, more realistically track the ISM. So this included new models for star formation, new models for gas cooling, and SAM. In EAGLE, effectively the lowest temperature you can get to is around 10 to the 4 Kelvin, so you're smooth. With this clumpier ISM, you kill off those low mass clusters. It's telling us something. It's telling us specifically that it is the way in which cool, dense molecular clouds are able to form that shape this low mass end of the globular cluster population. So the shape seems to be universally peaked in all of our simulations, as well as in nearby Milky Way-like galaxies. It peaks around a few 100,000 solar masses, and that is all through the influence of the differential efficiencies in forming clusters, as well as the differential efficiencies in destroying clusters.
Is this why you told me that the particle size and the SIMS was 10 to the 3, basically?
Yeah, so
I'm just wondering how you can resolve
we don't.
disruption of something
We
that's
don't.
only one particle.
Yeah, so
Do you count interactions?
this is, I'm glad you asked that question because I was avoiding going too technical, but now you've given me an excuse to explain how this works. So yeah, this is a really good question. How I said we did this, but I didn't say how. So here's how we do it. eMosaics has a mass resolution for the gas and stars of around a few by 10 to the 4 solar masses. So that means that this doesn't make any sense. And the reason it makes, the way we get away with this is we don't actually track globular clusters by forming multiple star particles that orbit around each other. What we do is every time a star is formed, in addition to all of the usual star formation criteria that go in, we calculate from the gas that star forms, what was that gas's pressure, metallicity, etc., and based on the cluster formation efficiency model, as well as the truncation masses, we populate each star particle with about 100 potential clusters. So we're kind of Monte Carlo sampling this. Then as that star particle evolves, it's moving due to its initial motions and the gravity from all of the other stuff in the simulation. Every time step, that star particle calculates a tidal tensor around it, which it can do from its the gravitational field that it uses. And that tidal tensor you can use to estimate the heating rates for tidal evaporation. So even though this, the one particle is basically here for us, each of those star particles can contain a population of clusters that was formed based on a model for how cluster formation efficiency tracks with gas properties, and then has been disrupted with a model that tracks how tidal shocks, which again you calculate with their tidal tensor, cause mass loss over time. So you start out with a lot of globular clusters, and some of them might be heavy, and by the time you end, one star particle might have lost all of its globular clusters that are attached to it. What Marta, I don't want to speak for her, but one of the things Marta is working on right now, which is hyper ambitious, is basically doing this right. So it would have to start with a small simulation of something like a dwarf galaxy, but actually resolve, if not individual stars, at least clumps of a dozen or so stars, as well as the internals of the molecular cloud. But I don't want to talk too much about her project because I don't know how far along that is. Yep.
So in words that a simple-minded observer biased to the local universe may understand, you are claiming basically that this is the equivalent of infant mortality at very high densities?
Yeah. I think Dietrich sometimes calls this the cruel cradle effect. That the high densities required to make big enough clusters at high efficiency, unfortunately also are exactly the kind of conditions required to rapidly disrupt them due to tidal shocks from ISM structure. Yeah. So I would also be remiss if I didn't mention other people's work, because we are, of course, not the only people who have looked at this. And one of the things I think that's really important to complement studies like eMosaics are things like what Marta is working on now and what Flora has worked on now. Simulations at much higher resolution where you can start to probe the detailed structure of both clusters and the ISM. So I think this bullet point turned into much more discussion than I was planning on, but thank you, because I'm a numericist and that's what I'm excited about. But if your star particles are 10 to the 5 solar masses, that means that you're basically at the same mass scale as the entire cluster already, and you're also not doing a good job of resolving the molecular clouds that these things form out of. So really you want to go down to like lower than 1,000 solar masses if you can, so that you can start making clusters that are made of hundreds or thousands of stars and are formed out of gas clouds that are also composed of tens of thousands of gas particles or so. The problem with doing this, basically the difficulty, I would say, with doing this is it's very expensive to run a simulation like this. A Milky Way at 100 solar mass resolution run to redshift 0 probably will use as much CPU time as you could pay for with a down payment on a house. And the other thing is, even at these high resolutions, you're still not going to be able to fully capture something you could do with, say, a direct n-body code where you're resolving every individual star, including hard binaries and things. But you can do a lot of things that e-mosaics can't. So something like this, where you can use the individual star particles in your cluster that you resolve to calculate properties that aren't cluster averaged, like velocity dispersions, is impossible to do in the Milky Way. And so, like, you can actually make comparisons like this for the stellar velocity distributions or the metallicity of individual stars that could have multiple populations. This is another major limitation of e-mosaics. We have no way of doing multiple populations because we have one formation event and it's all unresolved. So if you have 500 stars in your globular cluster, half of those could potentially be enriched from the ejecta of others, which could give you the multiple populations, which is a really important and interesting question in globular cluster formation. So I don't want this talk to just come across as there's only one way to do this in theory. This is really something that has to be a community effort. So just to recap, before we end for some questions, I don't think it's actually should be that controversial to say that at least some, I would argue most, globular clusters are just the relics of what the kind of star formation that happens at redshift 2 looked like. That it was in clumpy disks at high pressures and cluster formation efficiency was efficient. But actually tracing that to redshift 0 really, really heavily relies on understanding disruption, so tidal evaporation and tidal shocks. And so the environmental dependence of these disruption and formation events can make the globular cluster population you see sensitive to galaxy formation history, and you are able to tie these things together. So understanding the one helps you understand the other. Cool. So I hope some of you have some questions for me. Oh, yeah.
Okay, so for your subgrid model, you've mentioned that for the slow process of tidal evaporation, you do that was it tidal tensor?
Yeah.
To get a tidal heating like a probability in the Monte Carlo. So what about the fast process that you've talked about earlier?
That is the fast process, actually.
That's the fast
one. Tidal shocks is the fast process.
Right.
The slow process is evaporation.
Yeah.
And it doesn't rely on tides. So evaporation is an internal process to the cluster. It depends only on the cluster's mass and radius.
So is that being incorporated into your subgrid model too?
Yeah. Yeah, so really there's actually 3 mass loss mechanisms involved in the subgrid model. There's the fast tidal heating mechanism, there's the slow evaporation mechanism, and then there's the one that's like, oh yeah, of course you have to include that. Stars die. So just stellar evolution is the other one.
What about feedback?
What about feedback? Like, do you mean in terms of like
Do you
mass
put-
loss?
I'm actually quite, because I never worked on subgrid models, I'm just quite curious about how you actually do them and put them into high resolution, really high resolution simulations.
How much time do you have?
Sorry.
No,
not 10
don't
hours.
apologize,
Not
please.
10
In
hours.
fact, I'll give you a short answer now, and if you'd like to have a long answer later discussion, this is my bread and butter. So the short answer is putting a feedback model into a galaxy formation simulation is a constant battle against taking the energy and momentum that is produced by that feedback and smearing it across too much mass. That's my opinion as to why we need these models at all. Because at high resolution, we're actually on the frontier of this. Some dwarf galaxy simulations now are high enough resolution that they don't have a subgrid model for supernova feedback. They just have individual stars that when they die, release 10 to the 51 ergs worth of heat in the nearby gas, and it just evolves using the gravity, hydrodynamics, and cooling solver that's already in there. The problem is if you smear 10 to the 51 ergs, if you put 10 to the 51 ergs in 100 solar masses, you get gas that's 50 million Kelvin or so, which cools very slowly. If you take that same amount of energy and put it in 10 to the 5 solar masses, you get gas that's 10 to the 4 Kelvin. So it's dynamically uninteresting, that your feedback does nothing. So the subgrid models are all attempts to allow that energy that has to, because of your low resolution, be put in a large amount of mass, do the dynamical stuff it needs to do, push gas around, drive winds, outflows, etc., without losing that energy before it has a chance to do anything. And there's multiple approaches. Again, I basically spent a huge portion of my career on this. There is no one right answer. And the other thing to be aware of too is there's different forms of stellar feedback. So how you model radiation pressure is different from how you model supernova. But it's challenging. I would say my short answer turned into a long answer, I'm sorry. It's challenging. We haven't solved the problem yet, but we're in vastly, vastly, vastly better shape than we were 10 years ago. So we're getting to the point where multiple different models and approaches are sort of converging on some things and also sort of converging on galaxies that look reasonable from observational constraints. 10 years ago, no one could make a Milky Way that had the right number of stars in it. Everyone's Milky Ways had 10 times too, well, maybe 5 times too many stars. And the better models and better resolution have been the reason that we're at the point where we're not talking about maybe someday we'll do a galaxy simulation that looks right. Oh, no, that's okay.
There's small-scale simulations where you consider the feedback being output from those, say, council simulations, considering the energy. Considering the energy that's being output from those smaller-scale simulations, and you take those to take the total energy output and smear over the entire simulation box of those small ones, and then turn them into a subgrid.
So using high-resolution simulations as a way of building your model is an approach that's out there. There's a couple of groups that do exactly that.
Okay.
Yeah.
Thank you.
No problem.
Hi, Matilde. But then you went very fast over the point of the several populations inside clusters.
Yes.
I see that now that clusters for you are very small, sometimes several of them in a particle, but do you think or do you plan in the future to include this, why this population, second and third population, or second population appears?
Yeah, I went fast over that because I don't know very much about multiple populations. It's one of the aspects I haven't really dived into. The thing is, I think the thing is right now, with e-mosaics, we wouldn't really gain much insight from that because it's very, very unlikely that the potential mechanisms that can give you multiple populations would have a huge impact on survival of the clusters. So really, you could take e-mosaics as we have it now and just paint on multiple populations based on if you have a model for multiple populations that depends on something about the cluster. You could use the clusters that are in the simulation to look at that. But I think much more interesting are these high-resolution simulations where you're actually forming multiple stars in the clusters, and then you're able to look at, especially if you go to really high resolution with individual stars, like 1 solar mass particles or so, then you can actually just do a CMD, a mock CMD for your simulated cluster, and see if you get multiple populations and tweak your feedback physics, tweak whatever happens to the cloud to see what does and doesn't produce those.
But just to close this, so you guess that this is not going to affect very much the survival or the probability?
I don't think so, no, no. I think it's kind of unlikely. Although, again, I'm not an expert on the multiple populations question. That there might be a way in which it does that I'm not aware of.
But thank you very much.
It was mainly to quickly add on that question. So in the plot you showed, that was from my paper.
Yes.
We actually see in our clusters indeed like 2 different stellar populations. We haven't checked it out, but basically within this mass resolution,
rather than the physical environment in the simulation. Whereas if you can actually resolve a cluster with multiple stars, you can, that's very cool. That's very cool. Yeah, this is a cool paper. Everybody should read this paper. Very cool paper. And not just because you gracefully lent me your laptop when mine crapped out.
So I think we're...
So you're considering energy output. What about momentum?
Both. We consider both out. Yeah, yeah.
Okay.
So yeah, most feedback mechanisms consider both of those things.
So again, it's momentum smeared over the entire.
Exactly.
Grid.
Exactly. Yeah.
Considering all the momentum and all energy have completely escaped out.
Yeah.
Okay.
Yeah.
Sure. Thank you.
All right, so we still have to save a bit of time for final discussion,
Absolutely.
I think. Speaker Ben again.
Yeah. And thank you. I want to have one last thing I say. I see, Rainer, you're back. I'm glad. I hope your teeth are feeling fine. But this is the last talk, and I know Johnny thanked Rainer yesterday, but we're at the end of this conference now, and I think we really should clap again for Rainer for putting together such a great program. Okay.
So I think we have a final discussion that will be chaired by Maya and Angela. Would you guys be amenable to the idea of just taking like a 5-minute break, bathroom thing, and just coming right back quickly so we can just clear our heads and get ready for the final thing?
Thank you so much. Yeah.
Good stuff.
Yeah. I'll send you some more stickers for your laptop.
while we wait, can the people who have prepared the presentation about small scales, you can set your computer.
I don't know how these photos, but yeah, they probably doesn't matter. Doesn't matter. You can do it.
No, then it's fine. No, don't change the order.
Okay.
The large scale. Just plug in one computer. Then you have all the slides in the same computer, right?
Yeah,
It's
so
a
the
Google. Yeah,
shared
perfect.
slide, so it doesn't matter. It doesn't
Yeah.
matter.
One laptop.
Yeah.
And it's all good.
Put one, and then we start with the large scale.
You have a HDMI? Yeah, I don't have them.
Okay. Maybe we give them the mic. I don't know if it's better than this one.
Or maybe if one holds that one and the other one. My title's no surprise. I'm happy to see that. Friday discussion shop.
Hola.
Works.
Okay, everyone, please slowly try to go back to your seat. We are not done yet. So Maya and myself met some group representative of the 3 group discussion yesterday. I have to say it was really fun and interesting. So we decided actually that we let people present their ideas and describe what they've been discussing yesterday in the group discussion. But I invite everyone to actually ask questions. Imagine that you are reading these proposals and you should assess them. So please be not mean, but critical, okay? And yeah.
Should we do questions after each one? I think
Yeah, it's better you ask a question. We discuss each group separately. Yeah, it's better. So
If you take this one, then I take this, and then we at least can.
So we give just the time to present, and then we ask the questions. So the idea comes out all at once.
Yes.
Okay, so hello. We are Antonio and Flor. We're representing the large scale group. Okay, so we are aiming for studying mostly galaxies. And that's it. That's the name that we have to for the proposal. That is everything, everywhere, all at once. We're going pretty wide. So the question that we're asking, what is happening at the universe? Obviously, it's galactic scale. So it's like we're like aiming for everything.
All at once. That will
Yeah.
be in the next generation of the project.
So the first thing that we are asking is like we are going to start talking about the observational part of the proposal. So Ben wants us to be a little bit more realistic because we talk a little bit about infinite resources and amount of time. So we are just asking for a far infrared space telescope, like continuing the legacy of Herschel. We even make the shape of the telescope. If we get serious into the part of infinite resources and time, I have this idea of a net of telescope orbiting the Milky Way, going from the radio wavelength to gamma rays, like making interferometry. It would take maybe a few million years to do it, but we can do it. So the first aiming for this telescope is to make a really big survey, multi-wavelength, aiming for the bigger number of galaxies that we can retrieve. Maybe not with the highest spatial or spectral resolution, but just to constrain a little bit the stellar masses, the environment, the morphology, the distance, its redshift, maybe the star formation rate, and the chemical composition, if we can see some emission lines, also the kinematics. And we take like all these data to make a projection of all these parameters of this dimensional space, just to see how weird the objects are based on all these parameters.
Yeah, and to add on this, so we're not only using the far infrared telescope to get this. It's mainly, this is a gap that is existing in the observations, what I've been told, I don't know. So basically, we should then now have almost all wavelengths at some resolution. So we can have this big survey going on.
Yeah, thank you for that, I missed it. Okay, so after the survey and constraining all these parameters, we're aiming for a follow-up with a higher resolution, and deepness. And we want to focus on the more regular objects, like having 3 times more regular objects around 1 sigma, that objects that go beyond the 3 sigma. Still in proportion, we still have more string order, weight ones. And just to see a little more of them, to see if there is something weird about the normal object that we call initially, and the normal things that we see in just to see with a better how they look like. Okay, so even with that, we cannot see, we know the galaxy are 3D objects, and we only see 2D with observation. So for that thing, we got the simulation, and all these constraints will help us with make better simulation that Flor is going to talk about.
Yes. So if I also can steal the stick for a second. Sure. So basically with the simulations, we're actually planning to do the exact same thing. First having a big survey, so think about a big box size, and then zooming into the weird stuff. So we have it both in observations and both in simulations. So because I thought if I would just tell you guys, oh, let's get 100 solar mass zoom in simulation, you might not know how intense that is. So this is a plot I stole for myself, so that's why some of the simulations I care about are like more distinct there. However, we were talking about getting a zoom-in simulations of really like 100 solar masses, which is outside the scope of my plot. And then I also have to be very clear that this one only goes to redshift 4.4. So if we would like to run this to redshift 0, we need those resources. So if we really go there, and that would really help us to maybe even probe stars over 100 solar masses, because then the high-end stars will be individual particles in the simulation. But first in the box, we didn't really decide on how big we want the box to be, so I put just a line. But really going again to like this 10 to the 4, 10, maybe even 10 to the 3 if we do a small box, maybe more in this regime, we would really go higher than ever been done before. I miss a couple of simulations here, but they're not above the line. So to really kind of show what we want and why it's cool, I thought I would put this in here. So to kind of put everything together, the idea is to get a big survey of observational and simulation, and then dive deeper into the special ones. And actually, we think from there, you get the more exciting research questions on why something looks like this or something works like that, or why do we see so many galaxies that are this at this redshift or at this environment. But the main question will be, how does the universe look like, or how is it working? And that's it for large scale.
Will you post your slides on the Slack?
They're already on the Slack.
Questions? How much resources do you need for that?
A lot. I know just that run. So basically, we would need to get a lot of CPUs and a lot of hours, and probably burn a lot of just forests down. But if we have unlimited resources, we can just grow them again. But unlimited. But it should be possible. And like, to be honest, I really think we should be able to get such a simulation in like 10, 15 years.
We have a telescope in space. We convert the entire planet in the computer, or is it large on a lower scale?
Oh, it's lower scale. I think we would be able to be there in like 10, 15 years.
Oh,
so it's doable. It's doable, but
extremely reasonable.
yeah.
So I'm curious about what motivated your choice of 100 solar masses as the mass resolution that you need to achieve. I mean, it's better than what we have, but what's the reason for that number as opposed to 1,000 or 10?
Well, 1,000 is being done now. Well, at Redshift 4.4, but it's not exciting enough. And 10, we would probably be talking about hundreds of years to get there, maybe even thousands. So 10, yeah. So 100 solar mass regime seems doable. Of resources in the coming years.
Oh, okay, so it's not motivated by any particular, like there's some phenomenon we can resolve. It's just an order of magnitude better than what is currently possible.
Well, we should maybe be able to get these like POP3 stars or like the highest massed stars to be one star particle, which is not been done in a cosmological zoom-in simulation. So you would actually already probe something completely new, but it's still doable.
Okay.
Doable.
Also, the data will be available to the whole community, because this is like kind of overwhelming for us. So it's like it's for everybody to make ideas or what to do with this thing.
Any further questions? Okay, if not, let's thank them again, and then intermediate scale people.
Same computer it should be.
Just next slide. Yeah. It doesn't look like the right file for it.
Yeah.
Oh.
What is this? Oh, it's right up there.
Oh, okay, that's weird. That's weird, but I can't see it here. Okay, never mind. You can hold them up. Yeah, I'll be here. Okay, I'm too short. I need to grow taller. No, I'm just standing on my toes now. So. Yeah, I'm tiny. You can just start first.
All right. Hi, my name is Savannah Gramsey.
I'm Cheryl.
And we are working on the intermediate scales. So to explain what our idea is the WINE survey, as we call it, which is the wide infrared / interferometric / simulation nuclear environment survey. So these are kind of the big questions that we want to have answered. For instance, how does an extreme environment, such as in the Milky Way's galactic center, affect star formation? What are the properties in the centers of galaxies? Is the IMF in the galactic center different from other parts of the galaxy? And is the Milky Way CMZ different from other galaxies? Plus, how do these different parameters that we might be able to simulate affect star formation?
Yes. You just do the observations after the
Yeah,
simulation.
okay. So for observations, the plan is to have something like what has been recently proposed for the JWST survey of the galactic center, but in more filters with more MIRI coverage, so that we can sample more of the SEDs of different stars to better figure out if a star is, what the mass of a star is, what the age of it is. We would also want to have multiple epochs so we could get proper motions of the stars, and for a lot of them to use multi-object, high spectral resolution spectrometer so that we could get line of sight motions as well, so we could actually have the full 60 motions of stars in the galactic center. We would also want to have a huge telescope so we can look at the properties of other galactic centers in other galaxies, and maybe even resolve them to a similar scale that we have in the Milky Way today. To sort of do that, one of the ideas is we could put a telescope on the moon, turn one of the moon's bigger craters into a whole giant radio telescope, which, even though that sounds kind of crazy, it's an idea that's been put forth before, and I think it would be very interesting to a lot of people to have that done.
We're not as crazy as this previous group, and we're good. Anyway, so yes, because observations and simulations should go hand in hand, and we're going to talk about the simulation aspects too. So first of all, what we propose is to do some very high simulation magnetohydrodynamic simulations of the molecular clouds in the central molecular zone. The reason for doing magnetohydrodynamics is because magnetic fields, they too play a very important role in threading the clouds and affecting the collapse of those gas. And another thing is we're going to be including multiple clouds in our simulations rather than just one single cloud, because we want to look into the cloud-cloud collisions as well, and also simulate the transfer of gas in between these clouds rather than just having one single them. Then to do this, we're going to scan some parameter grid. We'll try to limit that, despite we have unlimited resources. But I mean, more parameters just make your simulations more confusing. So that might not be always the thing that you want to do. Now, the thing, so we're going to limit it to 3 parameters here. The first parameter that we want to scan is the external potential. That's the tidal environment of the CMZ ring. So, for example, we can change the different mass distributions in the potential model, and which will lead to different locations of tidal compressions, as in the point where the cloud becomes compressed due to when it's passing through the pericenter. Yeah. And second thing that we might want to vary too is the temperature of the gas. That's to mimic the different heating sources that exist in the ZMZ environment. And the third thing that we want to do is probably the amount of turbulence. That's the initial velocity field that we impose onto our simulation domain. So these are, the parameter ranges are going to be informed by observations, which I'm not familiar with all, so I'm going to give it to you later on. So what we're trying to measure off from the simulations is we want to focus on the kinematic properties of the molecular cloud, which of course it subsequently affects the star formation. Now for kinematics properties, we have several things that we want to look into, for example, like velocity dispersions and also the spin angular momentum, which can be used for getting the rotation of the clouds and subsequently correcting the velocities maybe. And we can also look into the morphologies, maybe the filaments and directional filaments due to the compression. And we can try to match these two observations to see if we can reproduce what we see in the ZMZ. So in addition to that, what she was talked about just now, that we can link it to the extragalactic stuff as well, and that's we can see whether the results we got from the Milky Way actually links to the galactic centers in other galaxies too. So that's part of the extra thing of this project, maybe. Well, yeah, we have infinite resources. Why am I limiting myself? Okay. Yes. There you go. Thanks. Anything?
Thank you. So, questions, Mark?
So why the moon? I mean, other than the coolness factor, what's the advantage of putting it on the moon? Normally when people talk about going to the moon, it's to do very long wavelength stuff where radio interference on Earth is a huge issue. Is that the motivation, or is there some other motivation?
So if we can get a telescope on the moon, both the having a very large like moon crater as a antenna could increase our sensitivity, and also that is a really long baseline for any interferometric observations we would want to do, sort of turning this into sort of like an EHT sort of long baseline interferometer kind of telescope.
More questions?
Thanks. I think this is all pretty realistic. This is good. This is good. You are like you have the talent to restrain yourself and stick to good outcomes. I like it. Bit of not exactly self-promotion, but community promotion. Of course, part of that is being done. You know, it's Savannah from Adam. So the James Webb observations of the entire CMZ in infrared in multiple epochs and multiple filters. Hours, but we tried the first stack, we tried 140 hours again. Everybody, there's the James Webb Space Telescope white paper for the observations of the galactic center. It's on archive. We don't know, so this will be similar like ACES that Johnny described. It will be an open collaboration. Anyone can join also later. Of course, then it depends who does what effort or so. We would like to encourage you to, if you want to be part of that, you can always endorse the white paper. Just drop a note to Steve Longmore, to Adam Ginsberg, or to me. Yeah, so thanks. Please think about it. And we hope maybe we even heard rumors that they're trying to, for the large programs at James Webb, actually to encourage the community to write white papers. If that is so, we're actually a step ahead in the process. So let's see.
Any further questions or comments? Okay, in that case, let's thank them again. Now it's time for the small scales.
Hi, so I'm Michael.
I'm Tara.
And we'll be discussing the small scales. So we were discussing yesterday the sort of open questions on the small scales, looking at embedded cluster and protocluster populations, trying to look at their kinematics at very early stages, and determining the properties of protostars in clusters, especially massive protostars. This is a Spitzer image of an embedded protocluster in an IRDC, and this is from, I did not make this, is from our colleague Alison Towner, so this is where the credit is from. And this is sort of a table that she made using different SED grids to fit the properties of the central MISO, which is marked by this pink diamond here. And you can see that for the values of radius and temperature, there's some big deviations depending on which grid is used, and this has been attributed to sort of source confusion and trying to fit models for one protostar to multiple, and so we really want a mission that can observe these regions in higher resolution, and that could also potentially give us an indication on the kinematics. So this is the same region now, just a zoom in with ALMA at around 1 arcsecond resolution, so you can now see like the individual protocluster members, and so this is the kind of resolution that we would like to see, an arcsecond or less, but perhaps in the infrared where we can get more useful photometry.
So currently, the kinematic surveys, like the Gaias, cannot reveal the early stage of like protostars because they are mostly embedded in the dust envelope. So we are actually want to propose these Gaia-like missions at IR wavelengths with sub-arsec resolutions. So our proposal name is the STAR map, the survey of kinematic and astrometry of protostars in protoclusters. You can imagine that this combination of the words can become this acronym, but actually it is. And we also make these emblems using PowerPoint. So what we're gonna do? We want to try with this the survey is we want to detect the newly embedded protostars in clusters and associations. So this actually gives more big pictures of the demographics of the protostars because using only Gaias, it only shows the information of the evolved stars, but if we use the IR, then we can see the earlier stage of the protostars. And also, if we measure the kinematics of the protoclusters, we can answer about some fundamental questions in cluster formations and evolution. So maybe you can And this is something like some more challengeables. But if we have very, very good spatial and spectral resolutions, then we can estimate the kinematics of a Keplerian disk around the protostars. Of course, this is the gas kinematics, so it might be different from the stellar kinematics like the Gaia things. But if we can measure the rotational velocity of the disk around the protostars, then we can actually measure the protostellar mass that gives the protostellar mass functions, and it is also
just like we know we were discussing like using infinite resources, but just on the note of feasibility, the Spitzer image that I showed previously was from Spitzer, which has a magnitude limit of around 14 to 18 depending on the wavelengths. And the wavelengths in the sort of mid to far infrared, 4 to 8 micron. And then Gaia can currently detect proper motions of 0.07 milliarc seconds a year. And rate of velocities of less than a kilometer a second at a G-band magnitude of 17. And so we could, at 4 micron, again, similar to the sort of Spitzer wavelengths, get with a 1 meter telescope around an arc-second resolution, which is what we would want for resolving these populations. And the current Gaia ability to detect a 1 kilometer a second velocity at around 2 kiloparsec, which some massive star-forming regions or embedded regions are at those distances. So this kind of mission isn't so unfeasible, and we were discussing yesterday that there are some plans for near-infrared Gaia type missions from ESA in the 2040s. So this is something that could definitely happen at some point, which is exciting.
Questions?
It's a very interesting proposal. I just wanted to mention, as you said, that the Gaia Near Infrared is a project that has already been started, and it's in the process of collecting support from the community just now. The project is being led by David Hobbs from Lund University. So if anyone is interested in joining, I can pass them the webpage where you can register your interest and what you're ready to add to the collaboration. Of course, this is not exactly what you are proposing. It's near infrared. We are very limited by the kind of detectors we have. You have to note that Gaia uses detectors that are read continuously, and you cannot do that with current mid-infrared detectors. So you need someone to develop detectors that will be able to do a Gaia sort of thing,
because the only other way you have to do these things is going to the places and staring at them for a while and then coming back a few years later. And it takes a while to do the whole sky if you go like that. But yeah, okay, if anyone wants to start with what it's likely to happen, just drop me a line and I will pass you the link if you cannot find it. Huh? Oh yeah, okay, I will do that. Yeah.
White, yeah, I can post the link to that one, and it's WST. It's an idea of having a 40-meter or doing just spectroscopy, like LSST is doing survey, photometric survey. Then WST will have a huge field of view where you can do spectroscopy everywhere within that field of view. So it will be a huge leap forward for doing spectroscopy of everything. So join this initiative. You learn a lot.
So this is maybe also a general question for all of the observing proposals. The initial idea of infinite time, infinite money, of course, they've all been realistic, doable. They don't require magic. And I'm curious because that's also been true for the simulation proposals, but there's a really hard limiting factor for simulations, and in many ways it's worse than something like the rocket equation called Amdahl's law, and that limits the efficiency, or it limits the speed up you get by throwing more computers at the problem, and it basically means that for, say for example, Flora, you were mentioning GigaEris is kind of slow going at Redshift 4. I could probably give you $1 trillion and it wouldn't make it go any faster, because if you doubled the number of nodes, the communication between them would make the actual speed up non-existent. In fact, might make it even slower. So say the 1 meter 4 micron telescope, is there a similar limitation in terms of, like, yes, there's only so much you can squeeze in, say, a Falcon Heavy right now, but conceivably there could be bigger rockets in the future. What is the limiting factor really? Is it just what can you fit in a rocket, or?
For like space telescopes?
Yeah.
Well, I imagine that, I mean, and maybe other people know more about this, but sometimes like you inevitably get problems when you have like telescopes with huge diameters, because I know like on the ground, like the problems with like deformation and things like this are obviously well known, but I imagine that even for a space-based instrument, that like for such a large diameter, there will be variations from place to place on the surface that you might not get with a smaller instrument, and that could affect things. I imagine that this is the case, but maybe someone else can say more.
I think
To be able to do faster read, like the scanning mode that Gaia has, right? It doesn't make images ever.
Okay, so that's
So these things are moving across the detector, and it's calculating these blips or whatever, and Gaia's like spinning around, and we don't have that technology. We know how to send something to space that's 1 meter, no problem.
That seems like not the limiting factor.
But I think that's one of the main things. This infrared, developing detectors in infrared is hard. And new technology is hard. And if it weren't hard, we would have had infrared images 50 years ago. But instead we had, PCBs come first. And then
there is the antenna theorem. So if you want more throughput and more angular resolution, you will inevitably, your instruments will get ever bigger. So just think on the VLT, a camera now, a simple camera like Force, what does it weigh? A ton maybe. And now on the ELT, the stuff, I mean, you can't even hang it on the telescope anymore. You have to construct rooms for the instruments because they weigh 10 or I don't know how many tons. So that is a limitation actually that you have. So I mean, yeah, at least you cannot, you have to choose between angular resolution and field coverage. That is true, but for example, the infrared Gaia, I love it, but in the galactic center it will again run into confusion issues. By the way, you have a factor 10 problem here. It's
Oh, yes,
10 kilometers per second. Yes.
0.1, yes.
Or 0.1 milliards second.
I forgot to say.
So going back to the science case of the proposal a little bit, as well as constraining the protostellar mass function, are the resolutions and the capabilities of the things that you were talking about, would that be able to put any constraints on the protostellar multiplicity as well as just investigating the mass function? Yeah.
I think so, because like the problem or like that we illustrated was that like in these sort of, this is going from the whatever the Spitzer resolution of this image is to something like an arc second, and you're able to see, or like whenever you zoom in on these regions and try and identify like what was one source previously breaks down into multiple, and this is like, this happens every single time an embedded region is observed at higher resolution. Like what you thought was, you know, one big clump or one big core splits up into multiple, and there will be a limit. Like at some point you're going to reach like the, you know, the minimum separation you would possibly expect between two cores or like a binary system, but I don't think we're there yet. You can resolve, you know, sometimes binaries in images like this, but I think that if you went to higher resolution, they might split up into further multiples and that sort of thing. So I think that any instrument that goes to higher resolution at this stage will give you more, a better handle on multiplicity, because you will just see more sources, but maybe you can also...
My understanding is that the fragmentations can be happening at very different spatial scale, like there's fragmentation in core scales and with some small scale, even in the disk. And we don't know, as far as I know, we don't know if this can be just end up the gravitational boundary system or not. So yeah, there are some, I think there are many theories for to explain that fragmentations, but
And having a higher level of resolution, maybe they could put limits on the different different methods for forming multiple systems, which often take place over different spatial separations. It would be something else that would naturally kind of fall out of the proposal.
Hi, Matilde. This is a comment for the three proposals and for something that I think that we forget. If one gets infinite resources, we have great telescopes, we have great computers, and I would add to have a lot of people. I mean, to set a call for applications, and you get the best scientists, if possible, we steal them from other fields, and software engineers. I have had the pleasure to work for a limited amount of years with some very good software engineers now working at Google and other places, and this makes a difference in a group. So just take into account that there's a
Any further questions or comments?
We are really approaching the end.
Yes. So if we could...
Let's thank the small scales and everyone for putting forward these ideas. I wanted to say that Maya and myself, we actually yesterday looked at all the post-its that you added. And it's clear that you understand what we need in the future, and it's essentially put together the large scale and small scales. I mean, it's something that comes up. If you come here and read the questions, all the question refer to that, how to connect the large scale to small scale, which is what we cannot do yet. So, well done. And yeah,
We'll post them on Slack so that you have a record of them if you want to have a look.
We have photos on Slack as well. And Rainer, I think, wants to make conclusive remarks. Yes?
Thank you. Well, first of all, thank you, Maya and Angela, for setting this up, because I know it takes some effort to go along with it and organize everything. So you did an extra effort. Thank you very much.
It was a lot of fun, actually. They did all the work.
Yeah, so we're nearing the end, or we are at the end. So I want to say a few thanks as well. For example, Fernando, who has been holding station back there all the time. All the tutors, of course, for being here, for making the effort. That's a lot of work that goes in there. Some people come from as far as Australia, although I thought they sent us an Android, but now I finally saw Mark close his eyes for a minute, so he's actually real.
At the end of the week, it's just, the battery is drained.
So thanks a lot, everyone, really. I mean, also the program, and so that goes, some of the tutors have been 2 years before, and so they basically developed the program. I mean, I have to thank definitely the Severo Ochoa Excellence Program that our institute is enjoying. This is like a program that goes to like a few dozen institutions in Spain every 4 years. You get extra money, and we actually are building up a training program, you name it, Bayesian courses, neural network courses, star formation, galaxy formation, interferometry, many software courses, and that's only possible because we have these resources, which, among other, again, it's staff, because we have Alicia was there, she's not here, we have a support office, we have actually 2 persons helping. Since we are Excellence Cluster, we finally have 2 staff members who help organize these kinds of things and take care of all the paperwork, because it would be impossible otherwise. So I would like to thank that program. You've gotten to know Isabel Marquez, who's the scientific director. Now I've forgotten someone. Definitely, I want to thank all of you for making the effort of being here. It has been fun. It has really been fun. So it's always worrying at the beginning. And I think I have got everyone. Yes, I think I have. So thanks a lot. Have a good trip home. Speak well of us, please. And if any of you ever considers working in Spain or career opportunities or so, be welcome to contact us as well. So,
hey.
Thanks a lot.
Contact everyone, not just Spain. Okay, we declare officially close the school.